Looks like we're live. Hello everyone and welcome to yet another Azuzin session. Let's make a little bit of an announcement and officially start the stream. Hello, welcome. How are you guys doing? So let's do the usual red circle live on Twitch. And what are we doing today on Twitch at Television website? Today we are implementing back propagation in C. That's what we're doing today. I'm going to give the link to twitch.tv/studying, the place where we're doing all that. Twitch.tv/studying, and I'm going to ping everyone who's interested in being pinged. There we go. The stream has officially started. So for the past several streams, we were developing an NH, which is a simple hair-only library for neural networks, and we're doing that purely for educational purposes, right? So we're trying to explore the paradigm of machine learning, and the paradigm of machine learning is essentially a paradigm where you're developing a model that models a certain process, right, something, and you're not coding the model directly. You're not developing the model directly. You are essentially describing how the model has to behave, and the training process or the learning process is supposed to configure the model so it behaves as close to your description as possible. So that's basically the paradigm we're working with. It's a very new paradigm for me. I never worked with that paradigm before, but it's extremely fascinating, and that's what we're doing today. So, and for educational purposes, I'm doing everything from scratch. I'm using C, not touching any of the, TensorFlow or PyTorch or whatever the fuck they are, until I understand how this entire thing works. Right, and that's essentially what we're doing today. So we're gonna give the link to the nn.h right, to the chat, right? So let me quickly copy paste this entire thing so it's in the chat, and for people who's watching on YouTube, it's gonna be in the description as usual. So let's take a look at what we have in here. So we already implemented sort of like a hello world of neural networks. We implemented ZOR neural network. It's a very simple neural network that consists of like two input neurons, two hidden layer neurons, and one output neuron. And it's supposed to act like a ZOR gate, right? So I can even draw how it's supposed to look like. So I think it's a little bit better to understand if you just visually draw this entire thing. So the entire neural network looks roughly like this. So you have two input neurons, right? Then you have two hidden neurons and one output neuron. And since it's a fully connected neural network, that means all of these things are connected. Everything is connected, right? And essentially, this is sort of like the first bit that you put in here, right? And this is the second bit, and this is the output bit, and it's supposed to act like a XOR gate, right? So the way we sort of train this entire neural network is that we initialize all of the parameter of the neural network with random numbers, right? So each sort of like each neuron has its own bias, and each connection has its own weight and stuff like that. Right, and then the learning process basically just configures all these weights and biases until this entire thing acts like a XOR gate, right? So that's basically what it does. We can even take a look at this entire stuff. So we have a little bit of a training data in here. So we even have like a training data for OR, right? So it's actually easy to swap different training data if you want to train different gates and stuff like that. So let's actually build this entire thing. Right, so I'm going to do zor.c, and I'm also going to link with the math library just in case. As you can see, it built, and I want to run this entire thing. And as you can see, so what we have in here, it's printing the cost function while it's training everything. So it's doing, I don't know how many epochs it's doing. It's 100,000 epochs. So it's actually pretty slow in Emacs, because Emacs is not a very fast terminal, right? It's not a very fast terminal. So let's actually open like a real terminal, right? So so we can do that a little bit faster, right? And let's just do ZOR. And it goes through 100,000 epochs pretty easily, right? And these are basically final weights and biases of the neural networks, of this specific neural network. And this is its behavior. So this is what we're basically validating. ZOR 0, 0 is very close to 0, right? So it's very close to 0. 0, 1 is 1, 1, 0 is 1, but 1, 1 is 0. right? So as you can see, it works. And again, we can actually swap it out. We can swap out the data if we want OR. It's going to train OR. So let's actually just build this entire thing without, you know, running it, because we want to run it in a separate terminal. So, and I think I can do a half of the iterations. And as you can see, it acts like OR. 0, 0 is 0, right? So maybe I can even make it a little bit bigger. 0, 1 is 1, 1, 0 is 1, and 1, 1 is 1, right? So, and you can sort of model this simple sort of gates. So the way we optimize the cost function, we're doing a very stupid hack, right? We're doing a very stupid hack, which is called finite differences. I'm not sure how common this hack is. From what I saw on the internet and from what I could understand from like talking to ChatGPT, it is very uncommon. But I like this trick. I absolutely like this trick because it is so simple. It is extremely simple, so it just, for educational purposes, I think it's extremely like invaluable, right? Because it just allows you not to talk about back propagation and just focus on what a gradient descent actually is, even though it is very slow. You know what I mean? Right, sometimes like, so there's a problem. I think we discussed that recently, is that one of the cool things in math, one of the valuable things in math is its rigor. Math, it tends to be very rigorous, but at the same time, rigor is actually quite often bad for education, right? Because it makes a lot of things obscure for people who are not familiar with the concepts they're trying to learn, right? So, and it's kind of similar with, I think, performance in programming, right? In performance in programming, because people are trying to, like, you know, force other people to write as fast as possible, to like write the most performant algorithms without understanding like why, like where to move. I made an analogy in the previous stream, is that, right, demanding a person who's learning neural networks to write propagation, back propagation from day one, is like asking them to run as fast as possible without telling them direction, right? Essentially, you come to them and say, you have to run, you go to jump to the car and drive, but where do you drive? Like, I don't know, it doesn't matter, just drive as fast as possible, but you don't know the direction, right? So that's the analogy I like to make. So backpropagation is rather confusing, right, for people who were never working with this kind of stuff, and finite differences is actually super easy to understand, right, for educational purpose, but it's slow, right? It allows us to figure out the direction in which we can move, and once we figure out the direction, we can try to move faster, right? So let's actually do a recap of how finite differences actually works, right? So essentially we have a cost function, right? And the cost function is effectively a function of all of the parameters of your model, right, or neural network in that specific case. So here I'm going to denote all of the parameters as W, right? So, but usually you have like thousands and maybe millions and billions of parameters, right, in your neural networks. And in this specific case, how many parameters do we have? We have at least 6, and then 4, so 10. We have 12 parameters, I think. I think that's how many parameters we have in here. So if I'm not mistaken, yeah. So this is, it's actually less. I think it's, oh, it's 9. Yeah, I'm an idiot. I'm sorry. Yeah. Yeah, I think it's 9. Anyway, so essentially, and the cost function essentially tells you how well your model performs, right? So the higher it is, the worse your model performs. So essentially, what you want to do, you want to drive your cost function towards 0, right? So the smaller it is, the better for you. This is how you optimize, right? So, and essentially, what you want to do is you want to find the local minimum of that function. What that means? Let's imagine that our cost function, right? So if we plot our cost function, right? So the x is going to be the parameter, and the y is going to be the actual value of the cost function, right? So, and it's something like this. right? We initialized our model with a random parameter. So and that random parameter is somewhere here, right? So something like this. Right, so this is the initial value. And essentially you want to keep modifying your parameter to drive it towards here, right, towards the local minimum, and that's going to be sort of your trained model, right? So initially it's just basically W0, right, and this is like Wn after like n iterations you actually figured out that you have to move here. So the question is, how do you figure out where to move at all? Like, how do you even do that? So the way we do that is we pick some sort of epsilon, right? So we pick some sort of epsilon, a fixed small epsilon, and essentially what we do, we add that epsilon, right, to our, you know, to our parameter, right? And we compute a cost function somewhere here. Right, the cost function somewhere here, so we take a cost function of this entire thing. Okay, cool. So, and we want to see what's the difference between the modified cost function and the previous one. So we're going to take the difference in here. Right. So, and basically it tells us this value. Right. But we want to know, you know, the ratio between the difference of the value of the function and the value of the parameter. So we divide this entire thing by this epsilon, right? And that is basically the velocity of the function that tells where the function wants to grow, right? It roughly wants to grow in this direction. And essentially what we're doing once we got this entire thing, so we can call it, it's sort of like a difference C. We just take and add this entire thing to our parameter, and this becomes W1, right? And we keep repeating that thing. We keep repeating that thing, right? And we just pick some sort of like an optimal epsilon manually. We sort of like it's a magical value, right? So we try and like one epsilon, so it didn't really work. So we made it smaller, we made it bigger, and we picked the one that actually drives us towards the local minimum as fast as possible. But that creates like a little bit of a problem, right? So what if we pick too big of an epsilon, and basically we're gonna be jumping back and forth around the minimum, but we never actually reach the minimum. Right, and if we pick the epsilon too small, we may actually never reach the local minimum fast enough. And furthermore, the closer you are to the minimum, the you know, the more changes you have to have. So the sensitivity to the parameter actually changes over time. Some of the parameter, so the cost function is usually more sensitive, more to one parameters, but less sensitive to other parameters. And basically, this epsilon assumes essentially the equal sensitivity of all of the parameters. So it's very much not optimal, and it's you know, very imprecise as well, right? It's sort of a hack, right? It's sort of a hack, and because of that, people usually don't really use this kind of approach at all. Right, they usually don't use this kind of approach at all. So what people usually use instead, they usually use a gradient descent. A gradient descent. So let's actually try to explore the gradient descent. I wonder if we can switch to something more convenient than you know, than my paint. Maybe we should switch to something like LaTeX, right? So I used to do like a mathematical explanation using LaTeX. So I think the time has come to get back to that, right? So I think I've got a couple of subs, so I think I would like to acknowledge them. Azura Kimura, thank you so much for gifting one community sub. It was 4 days ago, but I still want to acknowledge it because, you know, Twitch shows me that. 28 Grace Slater, thank you so much for Twitch Prime. Ice Leo, thank you so much for Twitch Prime with the message, yo, more machine learning indeed. That's right. I'm gonna do like even a couple of more streams, right? So I have a couple of ideas for this specific series. Low and C, thank you so much for Twitch Prime. Thank you, and welcome everyone to an epic artificial intelligence stream. And we got another sub while I was actually acknowledging other subs. Damned Me, thank you so much for Twitch Prime subscription. Thank you. Alrighty, so let's create a LaTeX document where we're gonna do our exploration, right? So we're gonna call it grad.tech, right? So I'm gonna try to remember how to use the later, right? Because I haven't practiced for quite some time. So I think you do document class, right? So you do document class, and you say that the class you do is article, and then you say something like, this is where you start the document, and let's do a section, and then in that specific section we're gonna say gradient. This is very fun. Descent. How do you spell descent? Descent. Yeah, I think I need to Google that up because I don't speak English. Right. Did I spell that correctly? Yeah, I did. Okay. I actually know English. How about that? How about that? So, how do we actually, you know, so I want to rewrite this entire formula, but in later, right? So to do that, I think align environment is not available in the later right away. So we have to do PDF later grad tech. So I think it's going to complain. Yeah, so there is no such environment. Okay, so I think this environment is located in a package not AVS but AMS math, right? So, and this is where we're going to have this kind of stuff, right? So let's do PDF later. It still doesn't have a line. Paragraph ended. Oh, this is because it wants to have something. Okay, so let's actually start defining something, right? So we're gonna have the difference in the cost function equal to you know, the cost function of the current parameter, right? So maybe we can call this current parameter as WI plus some sort of epsilon, right? Some sort of epsilon minus the this thing without the epsilon, right? And we're going to divide this entire thing by the epsilon, right? So that's basically the idea in here. Right, is it going to actually allow us to compile this entire thing? And it seems to be working. It seems to be working. So let's do mu PDF, right? Mu PDF. There we go. So to not flash bang you, I think I'm going to invert the colors, and this is basically what I wrote in my paint, right? So I think it's clear, right? So it's big enough. So I think I can even split this entire thing sort of like this. Okay. So, and essentially, doesn't this formula remind you something, right? Doesn't this formula remind you something interesting, right? Doesn't it look something familiar? So, essentially, right, this tells you, yeah, people who know this kind of thing, they instantly said it's a derivative, right? So it's very close to derivative. Here's an interesting thing. So the value of DC, its sort of precision as the actual direction of the function depends on how small epsilon is, right? How small it is. So, and what if we make it infinitely small? Not equal to 0, but infinitely small, right? We basically gonna try to do a limit, right? So, but I don't remember how to use limit in later. Later limit. So later limit bound. Okay. Oh, that's actually pretty good. So we can do they have to do underscore? I don't remember. No, I don't have to do underscore. Okay. So we can say epsilon, right? Epsilon to 0, right? So maybe it will probably also make sense to do something like I, right? Because it's sort of like an iteration. But maybe I'm not sure if it makes sense to actually have this size. So let's remove it to make it a little bit less noisy. And let's try to recompile this entire thing. And what? Am I an idiot? Oh, it has to be with a slash because it's a command. All right, so it's a command. Yeah, there we go. So, and essentially this looks like a definition of a derivative, believe it or not. If you just Google up derivative, right, derivative, and we go to Wikipedia, that's literally the definition of derivative. That's literally what a derivative is, right? So, doesn't it look like what we just wrote? Right, so here we're talking about some sort of abstract function, and instead of epsilon they use h, but they still drive this h towards 0, right? So, and basically what this thing does, it tells you the sort of like a velocity of the function in one specific point, w. So that's basically the derivative, right? So we can even write it like this, right? And if you use an actual derivative, right? If you use an actual derivative, so people tell me that the underscore is missing. Yeah, it's much better. If you use an actual derivative, you are moving towards local minimum precisely, because that's like precise thing. But here's the interesting stuff, right? So here's an interesting stuff. Let's actually go back to the original simple example, right? To the original simple example where we had a model with a single parameter w, and we were trying to find that parameter, right? So do you guys remember, like, if we take a look at the stuff from the first stream, right? So we have ML nodes. I think I'm gonna give the link to ML nodes in the chat and also in the description, so you can find the stuff in here. There we go. And so let's go to the description in here. So ML nodes from the first stream. There we go. So let's actually go there. So ML nodes, and we have a model in here called twice, right? And so basically we're trying to train a model that predicts this data, where the first column is an input and the second column is an output. And you can clearly see that this model is supposed to just double the number, right? It's supposed to double the number, it's supposed to multiply by 2, but we don't know that. So what we did, we just assumed that model has, you know, sort of like a general form of essentially y equal wx, and w is the parameter of the model, right? A single parameter of the model. I suppose in this specific example I also added a bias to sort of like a fully simulate a neuron. Why not, right? So the actual model in here is basically w equal x multiplied by y equal x multiplied by w plus b, right? So to actually do the gradient descent, right? So the gradient descent is basically using an actual derivative instead of finite differences, right? So that's basically what people usually mean by gradient descent. It's just like you take a derivative at that specific point and you move in an opposite direction, right? Because derivative tells you in which direction the function increases, so you have to go in the opposite direction, right? So to actually use the actual gradient descent, we have to take a derivative of this function. And here is an interesting question: how the fuck can we do that? Right? There's like a for loop in here. Like, how are we supposed to do that? Right? There's also division in here and stuff like that. Right. So to take a derivative of this entire function, we need to write it sort of like in a mathematical notation, just to at least see how this entire thing is going to look like, right? So let's actually quickly do that. Let's try to write this entire model in a mathematical notation, right? So we can also take a look at how the model works, if anyone is interested. So we can just compile this entire thing. Right, just a second. I'm gonna do twice. There we go. So we compiled it, and we can do twice. And yeah. So essentially cost was starting at here, right? So this is where the cost was starting, and it was driving down until it, I think, became basically, yeah, very close. Right, it became very close, and we found sort of these two parameters, right? So the weight and the bias, and this essentially, if you plug them into the formula, it will multiply by 2, right? So it will multiply by 2. If we get rid of the bias, I think w will literally become 2, right? I think w will literally become 2. Maybe we should get rid of the bias for the sake of simplicity, right? So let's actually get rid of the bias. I think it's gonna be better, right? So that will require going through the compilation errors, right? So, but that should be fast, relatively, right? So here we don't have to provide the bias anymore. So none of that stuff is needed. Like this entire thing is not needed. This entire thing is not needed because it's a bias. So this is a compiler assisted refactoring essentially. New line. Okay, so now if I just try to run, and as you can see, the parameter like literally became 2, right? So we started with the parameter equal to 4, the cost was huge, and then we drove the cost down and it became this. It was not super precise, but that's not really the point. Anyway, so let's try to write it in a sort of mathematical form, because we can't really take a derivative of this entire thing if it's not in a mathematical form, right? So, right. And so let's create maybe some sort of a subsection, right? Subsection, right? Not subsection, but just subsection. So what I'm gonna put here, I'm gonna put like a twice in here. So this is gonna be twice. So let's go ahead and try to write the cost function. Let's say that the cost function has only one parameter w, and essentially what we're doing, we are plugging some sort of a, like we have n samples in here, right? So if we take a look at the code in here, so this is the cost, we have n samples and we are iterating n samples, right? So this is going to be n, and in here down there, train count, we divide it by n. So essentially what we're doing, for each individual sample, we are actually finding the square of the difference of the actual value of the model and expected one, right? So let's actually denote the inputs as xi, right? So because we have like several samples in the training data, and the output as yi, right? So since it's going to be sum, we can write it like this. So this is a sum, and we're iterating starting from 1 up until n, right? So we have like n samples in here, and what we do, we take the current sample I, right? The current sample I, multiply it by w. We don't have any bias in here. I remove the bias, and we subtract expected value, and we raise this entire thing to the power 2, right? So so this is essentially, we're computing the cost function, which is the sum of the squares of the differences, like right? So if the actual value deviates from the expected value too much, the square is going to magnify that difference. It is going to magnify the difference, and the cost function is going to like basically rise very, very quickly. Right, and after that, I need to divide all of that stuff by the amount of samples, because it's an average, right? So we're doing an average in here, so we divide it by n. So this is how you can mathematically write this entire function, right? So although it's procedural, you can like easily write it mathematically. And let's actually try to go ahead and see how it looks like. It looks like shit, by the way, right? So I didn't want to put a star in here, right? Because in LaTeX you're not supposed to do that. Right, there we go. And to be fair, this kind of fraction is just like makes it look kind of meh. I think I could have done something like 1 over n, like so. Right, so let me quickly do that. There we go. Yeah, that looks much better. That looks much better, right? Look at that. So this is basically our cost function, right? Essentially our cost function. So what we need to do, we just need to find its derivative. Like, how can we find its derivative? So let's like literally take this entire thing and put it like this, right? So I'm gonna put parentheses around this entire thing, and we're gonna do that step by step. Right, since we're using LaTeX, it's going to be much easier to do that in later than with the pen and paper or in my Paint, right? Because what I will be able to do, I'll be able to copy paste entire chunks of the expressions and move them around and show you mechanically how you're supposed to do all of that, right? So this is something that is kind of difficult to convey when you're like writing, like handwriting, because you cannot rearrange things like by just taking them and moving them to a different place. Here in the text editor I can do that, and I think it's a huge advantage when you're using LaTeX. So quite often when I do mathematical doodles, I just use this kind of thing to rearrange around. Use knock. Knock is not finished, unfortunately. Right, so I'm gonna finish it one day maybe. Alright, so this looks like scheisse, because they are not aligned by equals, right? I would like them to be aligned by equals. Look at that, look how nicely they are aligned. And kind of these parentheses look lame. I would like them to be as large as the expressions they enclose. So to do that, I think there is this left and right thingy. Look at that. Doesn't this look serious? Doesn't this look serious? Right. So like you look at this formula, and you're thinking, holy shit, they're doing something important. Holy fuck, he probably has a PhD in fucking nuclear physics or something like that. Holy shit, look at these brackets, they're so fucking huge. Holy fuck, he's a genius. In fact, I don't even know what the fuck I'm doing, right? So, in reality, I don't really know what the fuck I'm doing. And in fact, I'm going to Google a lot how to do this kind of shit because I don't fucking remember. Okay, so here's an interesting thing. How do you take a derivative of this entire shit? All right. So here we have some sort of a constant, and it's quite important to remember we're doing derivative relative to only this variable, right? Only to this variable. So we have two expressions. We have a constant multiplied by this expression, which is basically a function of x, right? So this entire thing, this entire sum is a function of x, and we multiplied it by some sort of a constant. So what a derivative of such expression would look like, right? So we can take a look at the derivative cheat sheet, right? So we're gonna cheat a little bit. Derivative cheat sheet. All right, so let's actually grab the first thing. Please don't tell me, professor, that I'm cheating on the stream. Okay, so do we have anything useful? And this looks like shit. Oh, there we go. This looks like what we need. Look at that. So you have... Is that a sufficient quality? Like, I don't know, like it would be better to maybe have... Yeah, this is shit, but I think it's kind of close, right? So you have an expression, right? So constant, a function of x, right? And basically you can put the constant outside of that specific derivative, right? So and essentially what it allows us to do, right? What it allows us to do is just move this entire thing like this. Look at that. So I suppose it would be even better to have an equals in here. Look at that. Yeah, so because we're sort of like chaining this entire stuff like around. So essentially this particular derivative like is not going to do anything to this specific constant. Okay, so now we have a derivative of a sum, right? So and effectively what kind of sum do we even have in here, right? So what kind of sum do we even have in here? We can think about this sum as essentially... so let me try to do something like this. X. Yeah. So we can say that this is x0, y0 plus x1, y1 plus, and how do you do like her h dots or something like that? I think this is how you effectively do that, right? So basically the rest, but I'm not quite sure. Yeah, there we go. So that's how we do that. So effectively you have this. So and a derivative of a sum, right? If you have a derivative of a sum, is basically a sum of derivatives, right? So this is what it says in the cheat sheet, right? So it's totally okay to cheat. Right, so they tell you that you're not supposed to cheat on an exam, but this is not an exam, this is a real life. You're supposed to cheat in real life, and in real life, everyone cheats. And if you don't, you have disadvantage. That's right. So that's as simple as that. Believe it or not, as simple as that. So it's not like, you know, it's unfair, right? You're not supposed to cheat, like everyone cheats. Literally, if you don't do that, you're putting yourself in a huge disadvantage, right? So it is what it is, and it isn't what it isn't. So effectively, if you have a derivative of a sum, it's a sum of derivatives. So which means that effectively I can move this entire parenthesis even further inside of this entire thing, right? So I can just say, okay, just put this entire left like inside in here, right? So, and what I effectively do, like I just basically told you that we can move this derivative like further and further inside of this entire stuff. So I don't really like how we repeat the sum a lot, right? So we keep repeating sum quite a lot, not gonna lie, but maybe that's fine for this specific case. So maybe we can come up with some sort of like a command that can allow us to reduce all that. Anyway, so here we have a square of a function of x, right? A square of a function of x. So what you're supposed to do with this kind of thing? So here we are getting into a territory of a chain rule, right? Right. So where is the chain rule? I can't really see. Chain rule and other examples. Yeah, there we go. So this is the most important formula that we can have in here, right? So that we're going to keep using throughout the string. It's a chain rule. It's essentially when you're trying to take derivative of two nested functions. And do we even have like nested functions specifically in here, right? Do we have any nested functions in here? Well, the first function that you can see is the function that takes a square of something, right? So we can say that the very first function is the one that takes a square of the thing, right? And it's an outer function, right? It's an outer function. And the inner function is this thing that multiplies the x by the weight and subtracts the w, right? So in this case, we can say, so x multiplied by w minus y, right? So this is basically two functions, right? This is basically two functions. And essentially what we have to do, we have to take the outer function, like the entire expression of the outer function, and basically move it outside and take a derivative of it, considering this entire thing as the single variable. So a derivative of square is basically 2 multiplied by this thing, right? So this is the outer function. We took a derivative of an outer function, right? Then we have to take a derivative of an inner function, like so, right? So, and let's actually recompile this entire thing. Let's recompile this entire thing, and it didn't work. Something is missing yet again, and this is because we have too many repeating things. So the line is 21. I don't see what's wrong in here. So it's supposed to be, oh yeah, it's because it's a double right in here. I think that's what it's complaining about. So let's remove this entire thing. Okay, so and now if I take a look at this entire stuff, there we go. So as you can see, what we did in here is essentially we took the outer function and took a derivative of it, and it's just basically to that specific expression. And then we take the inner function and we take a derivative of it. We didn't compute it yet, but we're going to compute it, right? And essentially this entire idea is if you have several nested functions, you just like peel off the layers of the function. So you compute the derivative of the outer layer and you sort of peel it off, and then you compute the derivative of the other layer and you peel it off, and you just like multiply them together. So this is how you mechanically do that, and you can do that with as many functions as possible, as you want actually, right? So that's basically what it is. That's how you take a derivative of this entire stuff. Right. And this is precisely the reason why I didn't want to show this entire shit on the first stream, because that will scare you away, because it's not very pedagogical, or how do you say that in English, right? So because the point of like optimizing the cost function is not about that per se, right? It's about just driving the cost function towards 0, right? But to drive it more precisely and more efficiently, you need to take its derivative, and derivative is just like the velocity of the function, and you have to go in the opposite direction, right? So yeah. All right, so I think we've got some subs and some things, some bits, I would even say. Azora Kimura, thank you so much for 100 bits with the message. There once was a man named Toding who sat down to do some coding. He steeped the tea and started the stream for another season of recreational programming. Thank you so much for 100 bits. Is that supposed to be some sort of a poem? I'm too stupid, I'm sorry. My brain preoccupied with trying to explain this stuff, right? So, and I might be missing something. I really apologize for that. Oh, it's a limerick. Oh yeah, you're supposed to read it as a limerick. So I'm really sorry, because my brain is really preoccupied with like how I'm gonna continue about that, because it's a kind of a, you know, interesting topic, right? There is a lot of details. It's not particularly difficult. It's just like there is a lot of details, and you need to get them right. Okay, so how can we get the derivative of this specific expression, right? So this thing here is actually a constant. So that means it doesn't really matter. So we can like straight up like remove this entire thing, right? Because it's going to be equal to 0 anyway. So nobody really cares, right? So nobody really cares. And we need to take a derivative of this entire thing. Right, and when you have a derivative of a constant and a variable, right, of a constant and a variable, the constant is basically, the variable basically becomes 1, and you're only left with a constant, right? So the variable in this specific case is w, because it's a parameter of the cost function. Well, it's somewhere here, but yeah, you get the point. So essentially, the result of this entire stuff is going to be x1, right? Is going to be x1, and we just computed the derivative of the cost function, right? So I would like to maybe even reiterate a little bit further, right? So we can basically put them side by side, right? So this is the original function, right, which is a sum, and this one is a cost function. So this one is a cost function. And we're going to put it like this, and let's just actually compare them together. So here they are. So this is how we compute the cost. So this is the first thing, and this is the velocity, like where exactly that cost is moving, right? So that's basically what it is. So what we need to do now to create a better learning algorithm is, instead of coding this, and instead of coding a finite difference, let's try to code this and basically keep subtracting that value from the current parameter, right? So that's essentially what we can try to do. Let's go ahead and do that. So let's literally try to code that. I accidentally closed it. Right, so let me open it one more time. You know what? I think I need to move the entire PDF document towards like ML nodes. I think I'm gonna actually move it in here, because that's where I'm gonna be doing all of this stuff. Right, so let me open new PDF. So here it is. So let's go ahead and like literally code this entire thing twice. .c. So here we have a cost, right? So here we have a cost, and let's actually introduce g cost, right? So for the gradient, or maybe d cost, right? Float w, right? And what we're gonna have in here, we're gonna have a result. So let me maybe split the screen into. Did I already close it accidentally? I think I already. No, I didn't. I'm an idiot. I'm sorry. Right. So there we go. So here it is. It's gonna be 0. So the actual n is in here is the train count. We are iterating through all of the examples, n plus I, right? And what we're adding in here, right? We're adding 2 multiplied by the current x. So we need to get the current x, right? So maybe we can even steal this entire stuff from here, right? So x is a train I, 0, and the expected y is 1. So here we do x multiplied by w minus y multiplied by x again, right? So because this is the derivative. Then after that, I just divide this entire thing by n, and there we go. We got the derivative of the cost function, right? Derivative of the cost function. So what's going to be the next thing? So here, right? So here we're just like taking the finite difference in here, right, by epsilon, but we don't have to do that anymore. So what we can do instead, we can do d cost w. There we go. And if I try to compile this entire thing, I think it's going to be kind of interesting, right? So the compiler is going to complain that we don't really use cost function anymore, right? So which is kind of interesting, right? So because we were computing the difference from this entire stuff. And another parameter that we don't use anymore is an epsilon, right? So we effectively don't need an epsilon anymore, right? And let's try to actually step only once, right? So let's actually try to step only once. Maybe somewhere here I actually want to print like the full thing, maybe even 0, right? So let's actually do 0, and I'm gonna do twice, right? So the cost is 83, it's pretty big, the actual value is W, but it's supposed to be 2. Right, what if I now step once? So it's using like absolutely random value. Let's actually fixate the value to something stable, right? So let's say 69. Right, there we go. So we have a cost that, and no matter how many times I run this entire thing, it's going to be the same. And now let's try to do one iteration of that specific thing. Right, so one iteration, looking good. We can, I think, even move a bit faster, or maybe not. Right, but as you can see, it actually drives the cost closer to 0. Right, it actually drives the cost closer to 0. So if we try to do like 10 iteration, right, it drives pretty fast. We can even take a 2. I think it's gonna go even faster. Right, there we go. Right, maybe even like 1. And yeah, if you take an epsilon of 1, it goes towards like 0 really fast. So it only took around, I think, yeah, 6 iterations to actually go towards 0 and became equal to 2 instantly. Right, so it goes there really fast. So let's say we're gonna have 6 of them, right, and it's like 2. Yeah, it's a little bit too fast. And I wonder, can we compare all of that with the finite differences? It will be kind of interesting. So if we do 0, right, so here is the original cost, and this is going to be float dw. So this is the finite differences. And in here, else if, and if, there we go. So, and we're going to put the epsilon somewhere here, right. There we go. So now we can flip-flop between this entire implementation. So this is the essentially gradient descent, right? So we're actually computing the actual you know, derivative, and here we're gonna use the finite differences, right? So and finite differences actually as fast you know, as the rest of the stuff, but it kind of, yeah, it still didn't reach like the 2 precisely, I would even say. So if we like make 10, right, it still doesn't really fully reach because the epsilon is probably too big. Right, the epsilon is too big. So if we kind of make like 50, right, it still couldn't reach it. Like as soon as the you know, step, like as soon as the function becomes too like sensitive to the parameter, epsilon is failing to adapt. Right, so because we got too close to the actual minimum, and the epsilon is too big, it just like cannot like jump over it, right? Because it becomes too big. The advantage of the actual derivative, of using actual derivative, is that as closer, if it gets closer to the local minimum, it becomes smaller and smaller and smaller, and it can get very precise, right? It can get very precise. So, and in case of the, you know, actual gradient, right, it can just like straight up jump here and just stay here for as long as possible. It's just a fancy root finding method. Yeah, exactly. Isn't like root finding basically a gradient descent, but it's a gradient descent with like a second derivative for some reason. I don't really understand the justification of this entire stuff, but yeah. I don't really understand the justification, but anyway. So, and as far as I know, computationally, computing d cost is actually faster than doing finite differences, right? Because you have to compute the cost twice in here, right? You have to compute the cost twice and just subtract it. Here, you basically computing a different function, but only once. So because of that, you're kind of iterating through the data only once. So maybe that also you know, contributes to like better performance. But I'm not a mathematician, I'm not an AI person, I'm just like talking out of my ass. But from my testing, gradient descent actually greatly improves the performance. It just like works faster, right? It generally you know, works faster. So yeah, and that's basically what it is, believe it or not. So this is basically how you're supposed to you know, optimize the cost function. You need to take the gradient, the derivative of that function, and gradient is basically the derivative, right? So right, so do you guys know what is a gradient and what's the difference between gradient and derivative and stuff like that? Right, so essentially when you take a derivative, it tells you the velocity of the function, right? So where it moves. But it makes sense when your function has one variable. What if your function has several variables, right? Like two variables, for instance. How we take a derivative? So what is the velocity where things are growing, where it's moving, or something like that? Gradient is basically a derivative for multivariable function, but instead of returning one number, it returns a vector that points towards the direction the function is moving, right? So for instance, you can even Google up what is a gradient, right? So it's sort of like a vector field, function gradient. Gradient is a vector. Gradient is a vector indeed. So you can Google it up, right? So if you have a two-dimensional function, essentially you have some sort of a field, right? So because where the variables are x and y, and the value of the function is like the third dimension, right? And yeah, so the gradient basically computes the derivative of this, and it just creates this sort of like gradient, like a vector field. So we have these two functions with like a local minimum and local maximum in here. Right, and because of that, this specific field moves like sort of towards this local minimum, and because of that, it moves like, though I think, yeah, so this is supposed to be minimum, right? So because the gradient actually grows towards the bigger value, right? And this is the minimum, and this is the maximum, right? It grows towards the maximum. So yeah, there's like two peaks in here. So it's basically a function that returns you a vector, right? So the derivative returns you like a one value, but in this case it returns a vector, right? And since our model can have many parameters, gradient is going to be vector with the amount of elements as the amount of parameters of the model, and you will have to subtract that gradient from your model, and your model can have 1 trillion parameters, right? So imagine a vector with 1 trillion elements, right? So that's basically how you probably train GPT-4, right? GPT-4 has 1 trillion parameters. So what they do, they compute a gradient, which is a vector of 1 trillion parameters, 1 trillion element vector, and they subtract that from the whole model. So yeah, essentially. So, and on a high level, this is pretty straightforward, right? So if you know derivatives, if you know partial derivative and gradients and stuff like that, you can just do that. But it's getting kind of complicated when the cost function grows in complexity, right? So when the cost function grows in complexity, it becomes really kind of complicated, right? So, and this is basically where backpropagation sort of comes into play. Right, so this is where it comes into play, because it basically allows you, it's a technique of computing the gradients and derivatives of a very complicated nested functions, and this is basically the cost function of a neural network. So that's basically what it is. Right, so but let's not actually jump too much into the complexity of like computing the gradient of an actual neural network. So let's start with simpler neural networks, right? Let's start with the neural networks with a single neuron. You can say that this is basically a neural network with a single neuron, but a neuron also has a bias and an activation function, right? So, so let's actually put something, let's go to the grad text, and let's introduce subsection 1 neuron model, right? So if I take a look at the right, so of this thing, so the actual value, right, is basically the input multiplied by a weight of the connection plus the bias of the neuron and some sort of an activation function, which in our case we're using sigmoid, right? So we're using sigma. So that's basically how, like, the model of a single neuron, right? The model of a single brain cell. So let's actually try to do PDF grad, right? So, and let's take a look at this entire thing. So this is how we do that. So we're not supposed to have this star in here. I don't think it makes any sense. Right, so this is a simple thing in here. And a sigmoid, right, so a sigmoid is a function that basically maps values from -infinity to +infinity to to values from the range from 0 to 1, right? It takes the minus infinity plus infinity and squashes it into 0 and 1. So that's what it does. So we can even define, right, the sigmoid in here, just in case, just to have it like in front of us when we're computing things. Right, sigma of x is, if I'm not mistaken, I think it's something like 1 over 1 plus e to the power of minus x. I purely like memorized this thing. Right, I think that's how it looks like, if I'm not mistaken. Yeah, this is basically how it's defined. It's not really that interesting for us, right? So it's not really that interesting. Right. So, and what's interesting for us is its derivative, right? Its derivative actually literally equal to itself, but not really. Multiplied by the sort of like inverted value of itself, right? So that's basically the derivative of this entire thing, and it's kind of useful to have in front of us, right? Because we will need this kind of thing when we're computing derivative and stuff like that, right? So okay, so this is a one neuron model, right? So we can even try to draw it using like ticks or something like that. Will be kind of interesting, right? So let's do. We probably have to do like a use package. Ticks, right? So let's put ticks. Right, and I think it's something like ticks picture, right? So yeah, there we go. Yeah, it works. It doesn't complain, which is nice. If I remember correctly, the ticks has this notion of like nodes, right? So let's put a node like at 0, 0, and you put like a text in here, and it will literally put the text in here. I didn't, yeah, so I didn't think it works like that. Oh, you forgot the semicolon. Yeah, you're supposed to also put semicolons in here. Right, so where is my compilation error? Compilation buffer, there we go, hello. But it's not centered, right? So we have to center this entire thing. My god, auto-completion poisoning, auto-completion poisoning, okay. So there we go, so this is hello. And I actually want to display it as a single neuron, right? So I think you have to do something like shape circle. I think it will work. Like it was something like, I don't know, draw, and you something like color or whatever. Like it's just like I'm going pure out of the intuition. Yeah, okay, it's so freaking stupid. Anyway, so. Okay, and here we have like two things, right? So basically the weight and bias, right? So this is the weight and bias, and this is the sort of the entire thing. Right, it also has activation function, right? So we can probably put this stuff in here as well. So we can put a sigma, right? But it's probably going to be too big. Yeah, but it's fine. Anyway, so we may want to place some parameters, right? We want to place some parameters at like -1, right? And in here we can say this is sort of like x, right? And then at +1 we want to put y, right? Something like this. So maybe I want to put spaces in here. There we go. But I honestly don't really want to draw anything around this stuff. Right. So, yeah. So let's put them apart a little bit. So maybe I can define some sort of a parameter in here, right, where we're going to have just one. And I'm going to put Emacs. It's more of a multi-cursor problem rather than Emacs. So now I can do something like 2. Yeah, there we go. So it could be actually half. Right, so let's put half in here. Yeah, there we go. So now what I want to do, I want to connect these things, and I think it's sort of like a path. Right, you also have to specify the names for these things, right? So this is basically X, this is a neuron, and this is a Y. Right, we want to do a path from X, edge, Y, and I think you specify like a direction or like what's an error or whatnot. Right, if I'm not mistaken. Well, yeah, it kind of worked, but it has to go towards the end. Yeah, there we go. So that's basically it. And then we're moving from N to Y, and we've got a single representation of a single neuron. How about that? Isn't that poggers? This is neuron. Doesn't look cool? I think it looks pretty freaking cool. That's amazing. So that's what we're trying to model in this specific case. That's very cool. So this is how we compute these parameters, and this is the definition of sigma, and all of that is going to be very, very useful, right? It's a one neuron model. So let's go ahead and create like a subsection, right? Subsection for one neuron model, and we're going to call it a cost, right? So what's going to be the cost? Right, so let's do align. So cost function, so here we actually accept two parameters, right? So W and B. And as we make our model more and more complicated, right? As we make it more and more complicated, we're going to have just more parameters in here. So I think we should basically drop passing parameters in here, because like it's just like it's not useful, right? So we have too many parameters in my opinion. Anyway, so we're going to have this fraction 1 over n, which I find kind of annoying to, like, you know, type out all the time, because we're going to be repeating it anyway, and it just like takes too much space, if you know what I mean. Right, so where is the cost? Here it is, right? So it's just that this is how much space it takes just to draw this specific thing, and it's just like not particularly useful. Okay, so what we want to do, right, we want to take the activation of that neuron for one single sample of the training data I, and we want to subtract what is expected, right, what is expected, and we want to write that to the power of 2. Right, so that's what we want to do in here, and there we go. So we've got this entire thing. So the next thing we need to do, we actually need to start computing the derivative, but in this case we need to modify not a single parameter w, right, not a single parameter w, but also b. And this is where partial derivatives come into play, right? And partial derivatives are actually very simple, right? So essentially you say, okay, I'm computing derivative with respect to w. And what that means I treat w as a variable, and even though b is also a variable of this function, I just treat it as a constant, right? And I compute basically this entire thing sort of like with respect to this entire stuff. So I think it's done like partial, and then you have to put a fraction in here. the notation of this stuff is actually very annoying. So the difference of c with respect to the difference of w, right? So, and then if we put this parameter in here, so something like this, right? So we're computing something like this, right? And I find this particular notation kind of annoying. So partial derivative notation, right? Because it's kind of like noisy, like it's just like too much noise. But you kind of need to have a separate notation from the prime, because you want to specify that it's not just derivative, it's derivative specifically like with respect to this variable, because you can have a derivative with respect to different variables and stuff like that. So it's kind of important. So partial derivative, is there any better notation than this, right? Something more like, yeah, I would like to use something like this, but I like to have like a one single small thing that you can move around, and I kind of like this approach, right? Partial with a subscript of the variable that you're doing. I find these like sort of fraction style notations are kind of like too noisy. They're really good for job security, in my opinion. If you work as a mathematician or as a computer scientist, you can just like slap them around your entire paper, and it just looks impressive, and everyone, holy fucking shit, this person is irreplaceable because nobody except them can read that shit, holy fucking shit. So yeah, this is very useful for job security, in my opinion. But for explanation, it's not particularly useful because it's too noisy, right? So yeah, and because of that, I kind of like this one, right? Because it's a little bit more compact. It's still a bit noisy, but it's a bit more compact. So instead of doing that shit, what we're gonna say, right, so I'm gonna just remove it like that. And I'm gonna say partial, but with the subscript of the current variable that we're working with, right? So that's already better. But in the LaTeX itself, this is too big because we used to just move a single prime around, right? Remember how we were just moving it around, and like moving this like a huge thing around is not particularly pleasant as well. We can define like a separate sort of command. Let's call it partial derivative, like PD, and it's gonna have one single parameter, and we're gonna just basically construct partial underscore that single parameter. And now we can replace this entire thing with PD W, and that is a little bit more compact. There we go. So now we can just move this small little thing around. Again, right, so to take a derivative of this entire stuff, we could place it somewhere here. We could say PD W, right, and then left underscore, and then right underscore, something like this. And look how impressive that looks. Just look at how impressive this entire shit looks like. Holy fuck. Right. But we know that we can move it basically inside of the sum, because this is a constant, this is a sum. So we can just straight up take this entire stuff, right, this entire stuff, and move it inside of this thing. And that's basically what we have to actually compute in here, right? So, and another thing that I already mentioned, I don't really like how huge this entire thing is, right? So we keep repeating all of that, but it doesn't really convey too much information. We're going to be copying it everywhere. So I think I'm going to define some other function. Let's call it, so it's, what is it? It's basically an average sum, right? So it's an average sum, and it has two parameters, the iterator and the amount of iteration, right? So that's basically what it is. And the amount of iteration goes here, so it's basically n, and the iterator goes here. So now I can basically replace this entire shit with, avg sum. Why you keep asking me this shit? Okay. in, there we go. So that's actually a little bit more compact, right? So at least now this entire stuff is justified. There we go. So that's cool. That's very, very cool. Okay. So we're taking derivative of a square. So we have to apply the chain rule the same way we apply chain rules in here, right? So essentially here we have the outer function, which is a square. So we have to basically take that entire square and move it outside of this entire derivative, right? Move it outside of this entire derivative, take derivative of this entire thing, and then we have to take the derivative of the inner thing, right? We're taking the derivative of the inner thing, something like this. There we go. So that's basically what we have now, right? Right, but I forgot to actually move this partial derivative towards the left thingy. So now it goes like this. So we sort of like peeled off one layer of derivative and stuff like that. So basically, by the way, yeah, it starts with 0. It's supposed to actually start with 1. Thank you so much for telling me, right? Because we're mathematicians, and mathematicians start all of that shit from 1. There we go. So you see, like, there is another annoying, like, huge thing in here, if you can notice, right? It's like repetition of this expression of sigma x I w plus b. It's repeated 3 times, and it adds a lot of mental overload. Like, it's just kind of difficult to read this entire thing, because it looks like there's a lot of stuff in here going on, right? But it's actually not that much stuff is going on. Really, not that much stuff. So what if we factor out that specific expression into a separate variable, just like we do in programming, right? Even though we're doing math, we're still programmers, we're still engineers, so it would be kind of nice to factor it out to something else. Okay, so this thing is like related to the ith sample, right? So let's actually say that it's basically ith activation for the ith sample or something like that. And then we can take this entire expression, right, and literally replace it with AI, and boom. Look how much nicer it looks like. It suddenly became readable. You just like factored it out and it's just like, oh yeah, that makes sense now. Right? I think like factoring out shit like that into separate variables is just like so much valuable, because oh, I can now see shit, because before like I couldn't see shit in this mist. Right, but now I can. Wi and bi. No, we don't have to put I in here, because I is the ith sample, right? It's an ith sample. We have only one W and we have only one B, and they are not related to the samples at all, right? So that's why there is no subscript for W and B. Does that make sense? Because I denotes the current sample, right? So we're iterating from 1 to n, and we have n sample, and for each sample we just like, you know, add this sort of like a square, right? If that makes any sense. Anyway, so in here, right, in here, yi is a constant which is not related to w at all. So that means this entire thing really not needed, right? So it's a constant, so we can just basically remove this entire stuff. So the only thing that we need to compute in here is basically just this, right? So it's basically just this. So to be fair, I think I'm moving too fast. Like I usually have to have like to have some sort of a steps in here. So I think I need to put this stuff in here, right? And here, let's actually have PDW, left, right. Yeah, there we go. Well, I mean, probably we want to move PD inside of here, so it makes more sense. Yeah, there we go. So the first step was this, and then we like applied chain rule to the outer function, and we got that. And I think maybe we could remove the parentheses now. So the only thing we need to do in here is compute the derivative of AI with respect to the variable w, right? With respect to the variable w. So let's actually put it near in here. I think like it would be nice to keep things that are related to each other close to each other. So we have c and then derivative of c, and then we need derivative of AI. So let's put the definition of derivative of AI after the AI, right? So I think that would make sense. So PDW AI, and what it should be equal to, right? So that means basically what we have to do is just like take PDW like this, and I can probably even move this entire stuff like so. Right, so that's basically what we can do in here. There we go. So how we can do that? So as you can see, here we have two functions, right? Here we have two functions. So like the outer function is the sigmoid, and the inner function is this linear function, right? So, and again, since it's a nested function, we can apply the chain rule, right? So we take this thing, move it out, and take the derivative of it. But what is the derivative of a sigmoid? Right, so the derivative of sigmoid is the sigmoid multiplied by 1 minus sigmoid, right? So, and that means it's super easy. So here is the sigmoid, and we just multiplied it by 1 minus sigmoid. And we're kind of having a similar situation again. I thought we sort of like tucked some bullshit behind the variable, and it explodes inside of that variable anyway. So I think we need to factor out more things in here. What if we take a thing inside of the sigma, right? Inside of the sigma activation, and factor that out as well, right? Factor that shit out as well. Right, so let's say that something like value I is inside of this thing, right? So let's put it in here. So this is a value I, and now we're gonna just take like all of this shit and replace it with value I, and a boom, and suddenly we can read this shit. Okay, so that makes sense suddenly. Holy fuck. And of course, here we have to actually take the derivative of the inner thing in here, right? So there we go. Okay. So, and yeah, parentheses are probably not needed. So parentheses are probably not needed. So now we need to take the derivative of vi with respect of w. Right, and similarly as we did with AI, let's actually move, like define it like below VI, right? Let's define it below VI. So PD. So what's cool about this entire process is that you can do it purely mechanically. You can do it purely mechanically, right? So which is kind of nice. Though, oh yeah, some people say that maybe we should have not defined this entire thing. Yeah, that makes sense actually. So this is entire idea, like another idea that somebody suggested. Right. So let's actually go back. Yeah, maybe we didn't have to even do that. Yeah, that's nice. So essentially, since we know what it is, we can replace it with AI, and it kind of works out as well. Right, and the internal thing is going to be basically, yeah, that's even better. Thank you so much. Right, because that actually does not, like, we wouldn't have to define that stuff anymore. Yeah, thank you. And now we need to find the derivative with respect to, like, this entire thing. So the variable is w, so b becomes 0, w becomes 1, so we're only left with xi. Right, so we're only left with xi. So there you go. And, well, yeah, so we have to remove the derivative. There we go. So the derivative of activation I is this value, right? And so that means we can finally substitute this with this value, right? So we can literally take it, like in here, and just put it in here, right? But we want to actually put it on a different place. There we go. Cool. So basically, we found the first partial derivative of this cost function, and it's equal to that, right? And it's basically equal to that. But since we have two parameters, we have to do the same thing, but with respect to b. With respect to b. Luckily, it's actually really easy. Right, we basically can copy-paste this entire thing up until here, right? And the only difference is going to be is just instead of w, we're gonna have a b in here, right? And let's take a look at how would you compute this entire thing with respect to b, right? How would you compute this entire thing with respect to b? Let's see. So essentially, you can differentiate as usual up until here. And here, instead of w, you're going to have b as a variable, which means this entire thing will become 0, and this entire thing will become 1. So essentially, the derivative of this thing is going to be just this. So this parameter, just the sigmoid, without any, coefficient in here. So it's going to be just that, which means that the partial derivative of c with respect to b is just that, without any x or anything like that. And there we go. So we just computed both of the partial derivatives, and this is the things that you have to subtract from both of your parameters of your neural network that consist of a single neuron. We can probably maybe even simplify all of that and remove all of the intermediate steps in here, because I don't think they're particularly useful in this specific case, but maybe we can keep them. Right, so, and essentially, yeah, so now you have this thing that you can subtract from the weight of a single neuron, and this thing that you can subtract from a single bias of a single neuron. Right, and that's how we compute the gradient of this entire thing. So you literally have to just like go and compute that mechanically. All right, and once you got that, you can keep subtracting it from the parameters, and it will just go there. By the way, if you're going to be just using one of the frameworks, right? If you're going to be using one of the frameworks, they already have this implemented like for you. You don't really need to understand how to do all that. As far as I can understand, you just like tell you, like give your model to TensorFlow, and it will just automatically do the gradient descent on it, right? So here we're trying to just like go deeper into how to sort of like do your own gradient descent, right? And this is only a single neuron, by the way, right? As soon as you add another layer of the neuron to your entire model, it gets combinatorially more complicated, right? Because now you don't have like a single sigma in here, you have two nested sigmas. And it can become kind of like difficult to compute the derivative of such a like a complex expression, and this is where backpropagation comes in, right? This is where the backpropagation actually comes in, which makes it like mentally easier to sort of like think about computing the gradient of this entire thing, right? Okay, so, and as far as I know, the model that corresponds to a single neuron that we have in here is essentially the gates, right? So we have this little thing that tries to model the OR and 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 NAND gates, and we can try to implement dcost for this thing as well, right? So essentially what we did in here, so here we actually have two weights, surprisingly. Right, but it's kind of easy to add like more weights in here, I think. Huh. So our model is actually a little bit more complicated. So it actually has two inputs, right? So that means it has two weights, but it's relatively easy to modify this entire thing to support two weights as well, right? So it's going to be just a simple change. But we're gonna do that after a small break, right? So first I want to make a small break. I want to make a cup of tea, and after the break we're gonna just try to apply this approach to this specific model, right? Okay. All right, so let's continue, right? So let's continue. So we actually have two inputs, right? So we actually have two inputs. So we need to add these two inputs to our model, right? So let's go ahead and freaking do that. So this is gradient descent. This is a twice model, one neuron model. Let's update maybe the title, one neuron model with two inputs, right? So now we have two inputs in here. So to be fair, by the way, the weight is kind of related to the connection rather than the neuron itself. I put it inside of the neuron, so maybe we should actually put it somewhere on the connection. And I think it should be possible to do it like this. So we do node. I don't quite remember, but yeah, so we're gonna do node, and this is gonna be W, right? So that's how we're gonna do that. Let me try to do PDF grad tech. And it kind of worked, right? So first of all, it has to be mathematical W, right? So that's the requirement, and it kind of has to be, I think, above the edge, right? So it's going to be above, if I remember correctly. Ticks. Yeah, there we go. So, and since we're going to have two inputs in here, right? So that specific weight has to be like 1, right? So this is the first weight, right? So this is that. Epicu. So we have X, but I think I need to now call it differently. Okay, maybe not. So I need to locate this entire stuff like on a different sort of plane, maybe at an angle, right? What if I make it like higher, right? So because I want to have two inputs that go towards a single neuron. Yeah, there we go. That's a good one. Right, and maybe now I would say that the output is actually Z, right? So the output is actually Z, not X, because I want to use Y for the second input, right? So this is going to be the second input. So this is Y, but it's actually -1, right? So this is that, and now we can try to connect, right? So the path like this. Y edge, right? So this is node above W2. So this is the second one towards the neuron, right? And there we go. We've got this thing. Isn't that poggers? I think that's pretty freaking poggers. So this is the actual model that we have in here. Isn't that cool? Okay, so that also means that it has to be something like W1 plus Y, W2, and then the B. So this is the actual model in here. Right, there we go. So this is the activation. So let's update the rest of the stuff in here, right? Let's update the rest of the stuff. So XY, W1 plus Y, W2, right? So that's the actual thing in here. Right. So I can probably put this stuff in here. And then this stuff in here, and just remove this entire thing. So it's just like additional parameters, right? Additional parameters. And what's interesting is that the result of you know, this derivative with respect to w is going to stay the same, right? Because, well, I mean, almost, right? Since now we have two weights, we have to kind of specify that when we're referring to partial derivative with respect to w, it's actually the first one that we mean, right? So that's a very important point in here, right? But the result is still going to be the same because if the variable is w1, so the constant that we're going to have in here is xi anyway. And by the way, since we have like several samples, it has to be actually something like this, right? So it has to respect the current sample. Since this sort of like repeats the pattern, it should be super easy to compute the derivative with respect to w2, right? So we can just like copy paste this entire thing. Right, so let's put it somewhere here with respect to w2. And it's basically the same as this, right? It's basically the same as this, but instead of x, we're gonna have yi, right? So we're gonna have yi. There we go. Right, so yeah, so the first one is just sigmoid multiplied by xi, the second one is just yi, and b is just like nothing. And because of that, it is also super easy to compute the whole cost function with respect to 2, right, with respect to 2, and instead of x, we're gonna put y in here. So as you can see, it starts to like actually sort of like display some sort of a pattern. Right, so it's super, because of this pattern, it's super easy to just like add parameters in here, right? We don't have to recompute, like, you know, find the derivative over and over again. We can just see these patterns and we can just add things in here, right? So let's go ahead and just do that. Okay. So now we need to actually compute the, you know, the gradient of the cost, right? So, and the gradient, unlike the derivative, right? So if you have a function of several variables, that gradient has to return 3 values, right? So for each of this variable, we have to return like a new value. So that's what we have to do. So the way we're going to do that, we're going to have a function, let's call it gcost, right? So, which is a gradient. And we're going to just accept this entire stuff in here. And the output, effectively, the output is going to be the partial derivatives that we're going to have in here. So we're going to actually return them as the pointers, right? So we're going to return them as a pointer. Let's denote them as d. Right, so let's denote them as d. So it would be kind of nice. I want to kind of remove these intermediate steps, right? So kind of remove these intermediate steps, but I'm not sure. I think they're kind of useful just to see what exactly going on here. So I'm not going to remove them. Okay, so each individual partial derivative in here is basically a sum, right? So let's initialize this thing like this. So the first one is going to be 0. The second one is going to be 0, and the third one is going to be that. So we're starting to iterate through all of the samples, right? So 0 less than n is the amount of samples that we have in here, right? Plus n. So then we have things like xi, yi, and I think, yeah, I think I did a fucky-wacky in here. I changed the meaning of yi, right? Yi used to mean expected value. Now yi means the second input, right? So it means the second input. And the expected value in here is actually, has to be called z, right? So, okay, we had to actually refactor here a little bit more than I expected, right? So we have to refactor a little bit more. So, and essentially here, not that much. Okay, so that's actually pretty cool. Actually not that much. So we can just query replace yi with zi, except a single place, which is in here. Yeah, that's good. So now this is what we basically have in here, because the, as I already said, z is the output, so the expected output should be like z in here, but everything else is basically the same. So the reason why it was so easy is because we factored out a lot of things. So factoring out like complex and repetitive things is actually very useful. It just like makes it a little bit easier to, you know, to modify if we just need to add a new parameter in here. It's just like with the code, right? So math is basically programming without computers, basically. So yeah, it's just like the computer is the human who's doing the math, if you know what I mean. So when they verify that the thing is correct, they're basically evaluating. And as far as I know, there is like some sort of like a theorem that demonstrates, you know, similarity between proving a theorem and executing a code. Like something Horvath, something equivalence or something like that. I don't know anything about that because I'm not a math person. Right, so that's basically what it is. But anyway, right, so what we have to have in our code, right, is zi as well, right? And all of that is in the training data, right? So the train I, 0, so this is the first thing in here. And I'm probably gonna just copy paste this entire thing. So this is gonna be 1, and this is gonna be 2. Right, there we go. So, and what we need to do, we need to compute the first activation, I suppose, basically. Right, so we need to compute this AI. All right, so this is gonna be AI, and this is gonna be sigmoid, right? So xi multiplied by w1 plus yi multiplied by w2 plus b. So that's the current activation. That's the current activation. And then what we're doing w1 add this thing. So we do 2 multiplied by ai minus zi multiplied by ai again multiplied by 1 minus ai multiplied by xi. So we're just like, you know, once we figured out the formula, we just need to retype that formula into the code, and that's going to be basically it. Right, so for dw2, it's yi. For b, it's nothing. So because b is just like a one single thing without any coefficient, so that means it's going to be 1. So, and that's the entire thing. And what's funny is that this thing is like repeating itself. Right, this thing is repeating. We can maybe replace it with something like di. Right, so di equal, well, I mean, that's going to be basically that. Right, so it's even simpler than that, isn't it? I think that's pretty cool. So you may think that it's something complicated, but when you write it down like in code, it's just like, yeah, it's a simple thing. It's only like you have to do a little bit of a math and reasoning to like justify all of that, but at the end of the day, like in terms of a code, this entire formula stuff is actually super simple. Right, but this is just a sum. We need to do an average sum, so that means we need to take all of these things, right? We need to take all of these things and divide them by n, right? So that's basically what we need to do. Right, divide them by n, and that's basically the thing that computes the function. Yeah, thank you so much. Well, I mean, the compiler would tell me, but I mean, it's good enough. Right, so that's pretty straightforward. Okay, so let's see. So how the model works, right? So it's modeling something, right? So it's modeling something. We are basically have like a global variable train, and we're just setting either XOR or something else. So we know that XOR is not modelable by a single neuron, so let's put AND in here. Right, let's put AND in here. So as of right now, as I can see, we're just using the finite differences, right? So here is the finite differences, and let's see how well all of that stuff performs, right? So let's say we're gonna have like 100 iterations for this entire thing, and this is going to be just the gates. Right, this is going to be just the gates, and yeah, so this has to be dereferenced because we passed them by a pointer. That makes sense. Okay, so cost, yeah, cost didn't really, well, cost goes down, so here it is. I would like to maybe move the cost as the first parameter in here in the log. I think that would have been kind of useful. right? Because it being the last parameter doesn't really make much sense, right? Because I want to see this thing first, right? I just want to see this entire thing first. I think it would make much more sense. Let's go. Ooh. And there we go. So in the cost, it does go down, right? But let's now compare how quickly it's going to go if we're gonna use the finite differences, right? So I'm gonna do if 0. So here we just define that, which is fine. Maybe I can do the following thing. I can do dw1, dw2, db, and here we do not really do that, right? So we just like create them. And if. And in here what we're gonna do is just gcost, we provide w1, w2, b, and we get back dw1, right, it has to be a pointer, dw2 and db. So that's what we get back. And maybe furthermore, we have to repeat this process in here so we can actually move it outside in here, right? So here we're just like differently computing all of that, right? Differently computing all of that. So maybe we could even move this entire stuff to a separate function, right? So something with a similar signature as gcost, but actually dcost, right? So it's gonna be even more sort of like nice looking stuff. So, but this one is probably going to accept an epsilon. That would have made sense. So where are we gonna accept the epsilon? I suppose it could be something like first. So this is the epsilon, then the parameters and the dw in here. So, but here is also cost, initial cost, which we probably want to compute in here without any modifications, without any special modifications, right? So, and in here we can just do dcost epsilon w1, w2, b, dw1, dw2, db, and just remove all of that. So we can flip-flop between them. So as you can see, they kind of, from the point of view of an interface, they kind of similar approaches, right? So one more time, let's switch to this thing just to check that this entire stuff compiles. And yeah, that's how it works. The cost goes down, but it still couldn't find the end. I think it was the end, what we currently trained. We're training the end, so it didn't even come closer to the end. So if we switch to an actual gradient that we computed ourselves with our bare hands, will it go better, faster, stronger? Not really, right? But it's actually, I don't know, so we're moving with the same rate, right? So let's actually maybe do 1,000 of these things. After 1,000, it went relatively well, I think, right? It went relatively well. Right, if we switch now to finite costs, it's actually with this similar performance, actually, surprisingly, right? Maybe there's no even point to do all of that. But as soon as you start to do more complicated models, doing finite differences is going to be very imprecise and very computationally inefficient because you like need to compute the whole function. But actually, this is kind of interesting. Maybe like finite differences are actually very good approximation if you think about it. Until you need something more precise. All right, thank you so much. So let me take a look at the name. Last at the Vampire. Thank you so much for Twitch Prime subscription. Thank you. Maybe it is IO bound by writing to the console. Maybe we can actually check it out. So we can compare the actual time performance, right? Maybe that improves it, right? Maybe that improves it. Yep. So let's go in here and I'm gonna do the gates, right. So, and the time it takes is actually 100 milliseconds roughly. Well, I mean, it's pretty fast, right? It's pretty fast. So if we switch to, well, I mean, isn't that finite differences? Right, it is basically finite differences. Let's just recompile all of that. Right, and this is finite differences relatively fast. If we switch to the gradient, to the actual gradient, It's actually slower, surprisingly. It's pretty much the same. It's pretty much the same. Right. It is pretty much the same. But maybe if we get even more epochs, right? It's gonna be faster. It's just like around 1 second. And the coast is like 0.05, right? The coast is 0.05, finite differences. Yeah, it's around the same. I'm actually surprised that the performance is basically the same. The performance is basically the same between the, you know, the gradient and finite differences, at least on such simple models. At least on such simple models. And this is very interesting, I think. It actually depends. Sometimes it's faster, sometimes it's slower. It's kind of hard to put. All right, so, okay, that's cool. But how can you compute the gradient if you have two neurons, and not only two neurons, but the ones that are also nested? Because this is actually very interesting, right? This is actually very interesting. So let's actually go here, right? So we're gonna have so one neuron model, right? And here we're gonna have two neurons model with one input, right? So let's actually not make everything too complicated. Let's actually keep it at one input, right? So let's actually try to draw that specific model that I mean, right, with ticks and stuff. Right, so that's something that we probably want to have. So we're gonna copy paste the current model. And there we go. So I want you to actually do PDF later, grad tech, and refresh. There we go. So this is just like a one single neuron. And in here, let's get rid of y. All right, let's get rid of y. And this is going to be just like that. And x, let's keep x at 0. Right, so this is the first thing. This is the first thing. And now, what I'm going to do, I'm going to create this second neuron, right? So we're going to rename this first neuron to neuron 1. So there's 3 references to this name. We're going to introduce neuron 2. We're going to place that neuron at, I suppose, at D, right? Because we already have this sort of like a distance in here, which is kind of convenient in my opinion, right? So it is kind of convenient. But it's too, yeah, so it doesn't take into account the padding, right? It doesn't really take into account the padding. And by the way, from neuron 1 to, we have to move to neuron 2, right? So let's do neuron 2, like so. So that we'll put it in here. And Z, let's actually put Z at twice of the D. Twice of the D. There we go. And we're gonna move the Z path. We're gonna have an additional path from N2 edge towards the Z. And in fact, I would like to rename the Z to Y because we don't have several inputs in here. So this is gonna be just Y, and this one is gonna be just Y. Yep, there we go. So that's what we have in here. So we're gonna have 2 weights in here, right? We're gonna have 2 weights in here. So this is the first weight, and then on the edge between N1 and N2, we're gonna have another one, which is the second weight, right? Which is the second weight. There we go. So this is that. So the first weight, second weight, and in terms of biases, also we're gonna have here the first bias and the second bias. Yeah, there we go. So that's basically a different model. Though between 2 neurons, I would actually like to have a little bit more distance, if you know what I mean. Right. Maybe that's fine. Yeah, maybe that's fine. I'm gonna keep it like that. So here's an interesting thing. So there is a little bit of a confusion. There is a little bit of a confusion between subscript in this model and a subscript in this model. Right, and it's this kind of confusion I think is kind of important, because in this model subscript of W means the input, the weight of the input, right? But here subscript means the layer, right? It's a weight of first layer and a weight of second layer. Here it's a weight of first input and a weight of second input, and I think this kind of distinction is actually kind of important, right? And because of that, I kind of want to denote this kind of stuff slightly differently, right? What if instead of using subscripts, we're going to use superscript? When we denote the specific layer, we're going to use a superscript. I kind of got this idea from Thurlow and Brown from his neural network series, right? And I think it's kind of useful, right? So essentially, we're going to denote it like that. So as you can see, right? So it's a little bit more like bigger and verbose, but I think it conveys the point. So basically, a superscript is the layer and subscript is one of the inputs or one of the samples, right? Because here we use subscript to indicate like one of the samples or something like that. So I think, yeah, I would like to basically refactor those things to be like that. And I put parentheses around the superscript to denote that this is not sort of the power, right? So it's not the power of things. I think it's also quite important because it may lead to confusion, right? It may lead to confusion. Yeah, so I need to actually add Thurlow and Brown to the references, right? So 3b, 1b, and n playlist, and it's going to be done. So I'm going to put it in here as well. So thank you for telling me that. Right, so this one has to be 1. Right, so this is going to be 1. This is going to be 2. There we go. Oh my god. So we need to have like a bigger difference in here. So okay, what if I just increase the D? Right, so where is the D? I don't see where it's defined. Okay, so let's say it's gonna be maybe 2. Yep. I guess it's fine. So the only thing I care about is whether it's readable or not. And this is where it becomes kind of interesting, right? Because essentially, right, y is equal to, right? And first you have to take x and you have to apply the weight of the first layer, right? So applying the weight of the first layer and add the bias of the first layer, and then you apply the sigmoid to activate. It's actually sigma in here. Then to that, so you activated the first thing, To that, you need to multiply W of the second layer and then the bias of the second layer. And activate that again. That's what you need to do. You need to activate that again. And that is the model of this entire thing. We just added another layer, and now we need to compute a derivative of that. And that looks actually kind of daunting, but there is a trick that makes it a little bit easier, actually. Oh, so we got another sub. Thank you so much for aluminium. Sorry, I'm an idiot. Thank you so much for Twitch Prime subscription. Right. So essentially what we can do, we can factor out some of the layers, right? So remember how we, in the previous models, we actually took the entire sigma and we factored it out into like separate activations. What if we do the same in here, right? What if we say that this thing is basically an activation at the layer 1? It's a layer 1 activation, right? So it's a layer 1 activation and it's just like this. Suddenly it becomes kind of more readable, right? And it just like chains really, really well, if you know what I mean. Right, it chains really well. And you can think of y as actually activation of the second layer. Right, it's actually easier to think about this thing as an activation of the second layer. So you see something interesting is going on in here, right? Something interesting is going on in here. And here I can probably even actually replace y with you know, activation of the second layer, just to, you know, be consistent with all that. Right. So, and for the sake of consistency, we can also rename x as an activation of 0th layer, and it's sort of like a special case, but let's not do that, right? So yeah, so some people already say that an x is activation of the 0th layer, and the brain actually automatically tries to like find the patterns and generalize this into recursive formula, doesn't it? Right. So this is actually very interesting, right? As soon as you just like start factoring it out, you can see instantly pattern. Okay, this is recursive, but let's not jump ahead of ourselves, right? So let's not jump ahead of ourselves. Anyway, so essentially, let's try to compute the cost, right? So let's try to compute the cost. Even though this thing is like looks daunting, right? But if you approach it like very slowly and methodically, it actually like breaks down into like simpler and smaller problems quite easily. Right, so let's go ahead and just create subsection, right? Not mark, but just subsection, and this is the cost. Right, and let's start with the cost. And here is an interesting thing. So computing the cost for first W2 and B2 is easier than W1 and B1, right? Because in case of W2, so we need to take a derivative with respect to this specific variable. So that means this entire thing becomes a constant, so we can just like throw it off and we don't have to go in like deeper. So computing this kind of like outer variable first is a little bit easier. So we're gonna have a cost, right? So, and the cost is essentially just like average sum, right? So we have several samples in here, right? We have several samples in here. From I to n, right? So from 1 to n. And essentially what we do, we take the outer activation, so the outer activation, but activation in our specific case also has a sample attached to it, right? A sample attached to it. So because of that, I want to actually define this thing twice. So I also want to have like a subscript in here, right? So because this is an activation with respect to ith sample, it's activation for the ith sample. So this is quite important. So we have two nested loops in here, basically, right? In a cost function, right? So if we have something like cost function, we are first iterating samples, right? This is the outer function. We first iterate in samples, and for each sample, we are iterating all of the layers. So that's basically what we do. And that's why I kind of pass two things in here. So the subscript indicates the current sample, outer loop, and the superscript indicates the layer, inner loop. But we haven't defined the inner loop yet, right? So we just like do it like that. But I think it's quite important because we basically pass that I to x in here, right? So we pass that I to x and we pass it everywhere. So W doesn't have a subscript, right? Because it doesn't depend on the sample, right? And B also doesn't depend on the sample. I'm an idiot, right? So here, this has nothing to do with samples, right? It has nothing to do with samples. It's just like a demonstration. But to be fair, right, we want to denote yi as an expected value of activation, of the ith activation. So that's basically what we want to do in here. Right. So let me actually go try to recompile this entire stuff. So yeah, so this has to be, where am I? I don't see shit in this mist. I forgot to put a new line in here. That's why we can't see shit in this mist. There we go. So here we basically take the difference between an actual activation for the xi and the expected value. So, and that's the difference between the activation of the second layer and y. Y is sort of an expected value. And I'm not really sure, like in this specific example, like in here where we define sort of model, maybe I want to keep this thing as y just in case. Right, I think it makes a little bit more sense. So I'm gonna go back to y. Right. Yeah. So I think that makes a little bit more sense. But again, we're trying to be sort of rigorous or something like that. Okay, so this is basically the cost function, right? So this is the cost function, nothing particularly special. So as I already said, it's a little bit easier to compute. It's a little bit easier to compute the partial derivatives for the outer variables in here. So the weight of the outer function and the bias of the outer function. So let's quickly do that. Let's first do that. So this is going to be the weight, right? So this is the weight for the C. So we don't really know what it is yet. And then the B. There we go. Okay, cool. So what are they going to be equal to? What are they going to be equal to? We can kind of predict by effectively taking this entire sum, just putting it in here and saying that this is going to be that. So that's what we have. So let's go, you know, step by step in here, right? Let's go step by step. So this is a chain rule. We take the derivative of the outer function like so. So this is going to be just 2. This is going to be just 2. And then we take the derivative of the inner function, which I can't really see. Yeah, so the inner function doesn't include this thing. So then we can remove the parentheses. This is just a constant. This is just a constant. And now we just have this entire stuff. And there we go. I suppose we're ready. Yeah, there we go. So there's a lot of like superscripts and subscripts and stuff like that, but it is what it is, and it isn't what it isn't. It's kind of difficult to, you know, make it less job security-ish, if you know what I mean. So now we need to find the partial derivative for the weight of the second layer for the activation of the second layer, right? For the activation of the second layer. So here is the definition of the activation of the second layer. So let's try to put this entire thing in here, right? So how is it going to look like? That's the real question. That's the real question. So we can just put this stuff in here. It's kind of similar to what we were already doing before. It is kind of similar, right? So this is sigmoid, right? And that means that the derivative of sigmoid is sigmoid multiplied by 1 minus sigmoid. So that means we can just take this entire thing and multiply it by 1 minus this, and just take the derivative of the inner function like so. Right, there we go. So, and then when we take in derivative of this expression with respect to the weight of the second layer, so the weight of the second layer is in here. So the actual value is the activation of the previous layer, right? So what we end up with in here is the activation of the previous layer. Right, so we can put this stuff like this, and there we go. So this is the derivative of that. So it's the activation of the current layer, this thing, the sigmoid thing, and then multiplied by activation of the previous layer. You see how things start to chain with each other. Not just how the things start to chain with each other. It's actually kind of cool. Right, so there's another thing that we can quickly compute. It's the, you know, partial derivative for the bias. It's basically without anything, because bias is just like a single thing in here, so it's going to basically compute to 1. So, and we already have like everything in here, so we have both of these things. Right, we have both of these things. So that means in here, we can quite easily just replace this entire partial derivative with this thing, right? So with this entire thing, and basically call it a day. Well, I mean, for that partial derivative, at least. So, and this is what we ended up with, right? This is what we ended up with. So it's just like the usual thing, plus multiplied by activation of the previous layer, right? Activation of the previous layer. We can even probably get rid of all of the intermediate stuff, because I don't think it's particularly useful for that specific case. Or maybe it is useful, I don't know. Right, so, but let's keep it, let's actually keep it. Yeah. Okay, so for relative to B, it is super easy to compute, because it's literally this, right? It's literally this, but we just don't have this thing in here. Did it crash? Okay, it's literally crashed. Okay, let's do the PDF one more time. Okay. So the first derivative, the first partial derivative for the outer variable, for the weight of the second layer, is just this, and for the bias of the second layer, just this. It's kind of similar to whatever we had with the neuron, with the single neuron, right? So it's just basically that, but instead of the previous activation layer, it's just like straight up Y. Well, it's a wrong thing. So there's that. Well, yeah, Y is like X or Y, they are the inputs, right? So they're basically previous activations. Yeah, so they're basically previous activations. So, but now we need to compute shit like, you know, grad tax, weight for the inner, like partial derivative for the inner weight. So an inner weight is located like deep inside, like very, very deep inside. So I'm going to show you. So let's recompile this entire thing. Right. So if you take a look, so here is the activation of the second layer, then you go inside activation of the first layer, and in the activation of the first layer, only then you see W1. Right. So it's kind of difficult to go there. It kind of becomes very tricky to go inside because you have like one layer in there. Right. So there is an interesting idea that it's kind of difficult for me to express, but the idea is that you basically have not just a single cost function, but separate cost functions. You have a separate cost function for each individual layer. And for separate specialized cost functions for each layer, you can only compute the variables that are nearly accessible. Like in this case, for this cost function, it's like easy to compute this variable and this variable, but it's difficult to go inside. Right, so we can just basically introduce the following notion. Okay, so the cost function for the layer 2. Right, so this is the cost function for the layer 2, and this is partial derivatives for the layer 2. Right. Okay, so what does it give us? What exactly, what are we trying to achieve with that? Right. So if for this specific cost function, for the second layer, right, we can compute partial derivatives for weight and bias, can we compute partial derivatives for the activation of the previous layer? So essentially, we computed the partial derivative for weight, for bias, and we can't go inside of the activation. But what if we treat activation of this thing as a variable of that cost function and just like differentiate it? What will we get? We get basically an error, a difference, right? So the expected value was that, but we expect it to be different by that much. We're computing an error that we can then use to compute the cost function for the inner layer, and then another difference and for another layer, and so on and so forth. And this is where the idea of back propagation comes in. Does it make sense? So yeah, somebody says in the chat, so we have series of cost functions. So we have a cost function for the first layer, and then you compute like what are actually expected activations for the previous layer. Okay, based on those differences, we compute another like layer of cost functions, and so on and so forth, until we go to the input. And as we go, we basically compute partial derivatives for all of the weights and biases, and we know how to update them. So, and like we basically propagating this entire thing backwards. Does that make sense? It's the thing with this entire stuff is that it's very tricky to explain, right? Because there's a lot of like layers of complexity in here. It's not particularly difficult concept. It's just like a lot of things that you need to keep track of, and the only way you can actually get a grasp of that is by literally doing it yourself, right? So essentially, get that idea of, okay, so here's the cost function for that complicated model, and just like literally go ahead and try to take partial derivatives for that big cost function, right? And as you do that, you kind of learn, you kind of discover this recursive structure. You basically need to do it yourself to actually, you know, comprehend that. And if you don't want to do that, you can just like use one of the frameworks or something like that. But here, I really want you to understand this backpropagation, and it's kind of beautiful in a way, right? Anyway, so let's actually try to go ahead and right. And it's totally fine. If it's not clear, right? It's totally fine if it's not clear like what exactly is going on in here, because it's genuinely complicated, you know, topic, right? So it's totally fine. I tried to understand this thing for like 3 days straight. For 3 days straight, I was just like basically rewriting this specific derivative until I actually like found the structure that I can comprehend and I just like conceptualized. But essentially, yeah. Let's try to go ahead and treat this entire like previous layer, the previous layer as the variable. So that means we're going to have the cost function for the second layer, but the partial derivative is going to be activation for the ith sample, but for the previous layer, right? So that's what we're doing for the previous layer. So that means that we need to have in here, you know, a partial derivative for this specific thing, but for I of the previous layer, right? So how sensitive the activation of this activation is to the activation of the previous layer. All right, and this is rather interesting. So here we are supposed to have the coefficient, the corresponding coefficient. So if the AI is the variable, so that means the coefficient is going to be the weight. So here we have basically the weight of the second layer. So this is the weight of the second layer. So, and let's actually go ahead and just do that. There we go. So as you can see, like weight was not really a coefficient, it was the previous activation, but now it is a coefficient like that. So that means that that specific partial derivative is going to have this thing with the weight of the current layer as the coefficient. There we go. And here is an interesting thing. Now we need to define. So this is the you know, the cost function for the second layer. So this is the cost function for the second layer. What's going to be the cost function for the first layer? Right. So this one is rather interesting actually. What's going to be that? So we need to have an average sum, right? So this is definitely going to be an average sum. So that's for sure. Right. And we have the activation of that first layer. But what's going to be the expected value? Right, we have expected value for the second last layer, but what's the expected value for the inner layer, for the activations of the inner layer? Right, so here's the thing. So we know the expected value for this thing, but what's the expected value in here? Right, what is it? What is it? I don't know. We don't know the expected value of that thing, but we know the difference between the expected value and an actual value. And what's the difference between an expected value and an actual one? It's this partial derivative, actually. We just computed that difference. We just have it in here. So here we can probably do something like minus expected I, right? Let's put it this way, right? So let's say expected I. So when something went horribly wrong, so let me see. So it's just this thing, right? It's just this thing. There we go. Okay, so expected I, and let's just like define this expected I. What the hell is that expected I? It's just basically essentially the current activation, right? So the current activation minus, right, minus the current activation again, minus the difference that we just computed. So, and the reason why I'm doing it like that, of course, obviously, if you just like open the parentheses, you're gonna end up with that specific difference. But I want to keep the general structure of this cost function similar to the cost function of the second layer, so we can see the similarities. we can see the similarities. So I think it's kind of useful to actually think about it like that. Right, I do think so. Right. So, well, I mean, why is it? Yeah. So it has to be actually the first activation. So this is the first activation and so on and so forth. All right, so this is what we have. Okay, so we have the cost function for the inner layer, right? And so since it works with the inner layer, it is super easy to reach all of these variables, like weight of the first layer and the bias of the first layer, right? So, and let's just literally go ahead and do that, right? So let's partial derivative of weight of the first layer, right? So this is going to be the first thing that we'll need to compute. Might as well like just literally predefine them. So the bias of the first layer, and that is it, because we don't really have any more previous activations, right? So that's basically the only things that we need to compute in here, right? That's the only things we need to compute in here, right? And let's go ahead and try to tackle this entire thing. So it's going to be sort of like this. So I'm going to copy paste this stuff. So this is the right and this is the left. So I just want to see this huge formula, right? Not really huge formula, but the parentheses. I want to see the huge parentheses. And let's just go inside. Like I want to go step by step so we can see how this entire thing is going to work out, right? Hopefully. So this goes inside, and we need to do the usual thing with the chain rule, right? So we'll have to take this entire thing, right? Take this entire thing and put it outside, right? Put it outside and simply compute it like that, right? And then we need to take the derivative of the inner thing. So this difference, this thing is a constant, so we can just straight up remove this entire thing, right? So we can straight up remove this entire thing, right? And this thing becomes one of the things that we just need to compute at some point, somewhere up there, right? So it's basically the partial derivative for the first weight of the first activation layer, right? So, and here is an interesting thing in here, right? So we can simplify this expression because we know what EI is equal to. EI is equal to this specific expression, right? EI is equal to this. I'm an idiot, actually. I should have not put this stuff in here, right? So it should have been just like that. So EI was supposed to be just like the current activation minus this thing, and the reason why I supposed to do it like that is because when I'm basically shoving it into the I down there, like down there, it's going to play out very nicely. Look at that. Right, so you have something like this, right? So we have something like this. You open up parentheses, so this becomes plus. So let's remove one of the parentheses. So two numbers we subtract from each other, they become 0, right? So they effectively become 0. And what you end up with in here, right, is the derivative that we computed in the previous step, right? So here's the thing. For the cost function of the first layer, this is the difference. This is the difference. But for the cost function of the first layer, the difference is the derivative that we computed on the previous layer for that specific thing. Right. So, and this is how they chain together. This is how they chain together. So, but the only thing we need to have in here is just like the weight derivative for the first layer, right? The weight derivative. And it's going to be kind of similar to the previous layer here. It's just like, it's going to be one layer lower, right? So I'm going to just copy paste it in here. And while a layer lower, what do we have? We just have this previous activation in here, this previous activation in here, and here activation of the layer 0. And the activation of the layer 0 is xi, as we already said. So it already kind of generalizes kind of nicely, right? So it already generalizes kind of nicely. So for that first layer, right, it's going to be, it's supposed to be like a previous layer, but previous like zeroth layer is xi. And for the bias is just 1, we're just not going to have anything in here. We're just not going to have anything in here, and there you go. So that's pretty straightforward. So that means here, this is going to be just x1, right? So this is going to be xi, and this thing is going to be just that. Okay. And essentially, we computed partial derivatives for all of the 4 variables, right? Actually, we computed 5 partial derivatives. So we computed partial derivatives for the first layer, then an intermediate partial derivative, so we can compute the rest of the partial derivative for the inner layer. And if we had 3 layers, we would have computed another intermediate partial derivative to go even further and further and further and further. So we can try to somehow generalize this entire thing, right? So we can try to generalize this entire thing to arbitrary amount of like layers. So, but we're not going to have several inputs yet, right? We're not going to have several inputs yet. So, several arbitrary neurons model with 1 input. 1 input. So, here, right, I'm going to do a line. And what I want to do, I want to actually grab all of these definitions, right? But I want to sort of get rid intermediate steps because they kind of get in a way, right, and it don't really help, right? So we're going to just basically remove all of these intermediate steps so we can clearly see all of the necessary patterns that we then need to generalize in here. Okay, so here we have some sort of a forwarding. Obviously we can generalize this entire forwarding, right? So if we can even split this entire thing into 2 sections, right? So the first section here, we're starting from the input layer towards the output layer. So essentially here we define forwarding. So we're forwarding things, forward. And then here, when we're computing the cost function, we're computing things backwards, right? So we're computing things backwards. So in here, there's something weird. I just copy-pasted. I think I copy-pasted too much. So you're not supposed to have anything in here. So did I? Yeah, I forgot to remove some of this stuff. So it doesn't make sense. So what I want to do, I want to split this entire stuff, right? So here we're going to have end a line, and here begin a line. So in here we're going to have a subsection feed forward. This is the feed forward, and subsection back propagation. So this is the back propagation. Okay. So let me take a look at how it all went. Right, so this is a feed forward, right? So we basically define activation starting from the input towards the output, and back propagation, we are computing the partial derivative starting from the output layer towards the input layer. You're gonna share the PDF? Yes, of course. I'll show it at the end of the stream. Right. So yeah, here we're defining the activations. So essentially, how can we generalize this entire stuff, right? So I can just take this entire thing and I can basically replace, right? So if I is the iterator over samples, let's for the layers, say we're gonna have L, right? I think it makes sense. Well, L is the current layer. So let's assume that for this specific section, the current layer 2, so that means we're gonna replace it with L, right? So this is basically L. So that's what we have in here. And layer 1 is the previous layer, L minus 1. There we go. So, and then we need to have some sort of a definition, right? For like a special case of some sort. We can say that let's assume that AI0 is xi. And that's basically our recursive definition of feed forwarding, right? So the activation of the L layer for the ice sample is activation of the previous layer multiplied by the weight of the current layer plus bias of the current layer pushed into the sigmoid, with a sigmoid applied, right? And then you go backwards, and for that layer it's the same until you hit A0's layer, which is xi. And this is very much recursive definition. And for each of these things, this is how you compute their partial derivatives. Right, as you can see, you can basically derive this, generic recursive definition through whatever specific cases we had in here. Let's actually try to do the same thing for the backpropagation, right? So we have this thing, and let's try to also define it recursively, right? But this one is going to be a little bit more difficult, right? A little bit more difficult because that difference is basically this, right? So it would be kind of nice. It would be kind of nice to like replace that difference with this, sort of like right away, right? Sort of right away, so we don't have to have that. Okay, so that's pretty cool. And here is the thing. So you can see that to compute the cost function of the current layer, well, let's assume the current layer is 1, you need the derivative from the not really previous layer, but from the next layer, right? So it's a derivative from the next layer. To generalize this entire sort of recursive approach, we can say that this difference is actually derivative from the layer C3, from the layer 3. We don't have the third layer. We don't have the third layer, but we sort of imagine that we do, and that error difference is the derivative from that imaginary third layer. And imaginary, I'm not using word imaginary here in terms of like complex numbers or anything like that. I use it in the sense of like we're imagining things, we're just hallucinating things. So we have a last output layer, we're just hallucinating that there is another layer there, and that difference is basically that. That's basically what it is, right? So that, this derivative gives us the difference for the previous layer, and we already have the difference from the next layer that we computed sort of manually, if that makes any sense. So we can kind of say that, all right, let's assume that we're gonna have m layers, right? So we probably want to assume something like that. Let's assume that we have m layers, right? So we have m layers. I don't know why I put a semicolon here, but yeah. So, and essentially, when we are talking about that specific difference, right? So that specific difference, we usually have the following thing. So this is the current layer, and the cost is from the next layer. So we're gonna literally replace L in this specific case with M. So this is sort of like a difference from this thing. So let this, let's denote this specific difference, right. As this, right, or maybe even, yeah, like this. Let's denote it like that. Right, which will allow us to do pretty interesting shit. So in here, I'm query replacing 1 with the current layer. So this is the current layer. Boom. So then, yeah, 2 is the layer plus 1. Yeah, the layer plus 1. And now here, what we have, so the current layer is actually 2 now for this specific case, and 1, no, minus 1, I hope I didn't make any mistakes here. So that's roughly how we can generalize this entire thing. Right, so here we have for the previous layer and for this thing, we sort of compute it like that. And I think that's basically the whole formula for back propagation. Right. So, and the idea is the following, right? So you have some sort of data, right? So you're computing all of the activations and then all of the necessary like differences and stuff like that. And then you're going backwards, starting from the last layer and just like applying that. So you compute these two things, like the variables of the current thing. And here is, oh, god damn it. So I still have to put, yeah, I forgot about some stuff in here. Right, so this one has to be L. So some of the indices here is a little bit fucked up because I was not too, how to say that? Right, I just like missed some of them, but it could be easily fixed in the future. But yeah, so that's basically the recursive formula, which looks kind of scary. It does in fact look kind of scary, but this is because we're chasing too many indices in here. We're chasing too many indices. So we're chasing first the sample indices and then the layer indices. Right. So, but that's not even enough. That's not even enough because here we have only one single input and single output for each individual neuron, right? Single input and single output. What if we had more complicated neural network with multiple inputs and multiple outputs? That would become even more interesting, I think. So I don't really know why I closed it, right? Because I wanted to draw, like I didn't really have to close this entire stuff. So, right. So essentially, to actually perform this entire idea algorithmically, let's write some sort of like very like simple neural network. So we're gonna have something like this, maybe 4 things in here, right, and maybe 2 things in here, right? So let's fully connect this entire thing. Let's fully connect this entire thing. So this is a fully connected stuff. I think I forgot some of the connections in here, but it doesn't really matter. So they don't really have that much meaning, right? So they sort of like demonstrate the full connectedness of these things, right? So to do the backpropagation, so you're going to have 4 nested loops. You're going to have 4 nested loops. So the first outer loop is the loop from samples, right? For each sample from the training data. So this is the first loop, right? For each sample of the training data, you're going to be basically fast forwarding that sample until you get the output in here. And then you're going to be basically going backwards, propagating those differences in the activation layers. So now you have another inner loop, which is for each layer, for samples, for layers. And again, we had only one input and one output. So that means essentially what we did, we just followed that one path, right, in our mathematical expressions, that one path, and then followed back the same path. But here we have to actually follow back this path, and then this path, then like this path, then another path, all of the possible paths. So that means we're gonna have another for loop in here for current activations, acts. For current acts. So if your current layer is here, you would have another inner loop that iterates through each activation in here, right? Then when you're done with that iteration for that specific layer, you're gonna go here, and then you would have to iterate each individual activation in here, right? And then each individual activation in here. And for each activation, once you are iterating each activation, you would have to check each activation of the previous layer, right? So essentially, for each activation in here, you need to check each of these things. Then check in here, you need to check all of these things. So it's going to be another nested loop for previous activations. right? And by doing that, you need to keep propagating the differences and partial derivatives. Yeah, and that's basically, my friends, a backpropagation algorithm that nobody gives a shit about. And that's precisely is the reason nobody gives a shit about, because it's just like already implemented. But we can try to implement it ourselves, right? So we know the math, we know how it mechanically has to go. We can just go ahead and try to code this shit, if you know what I mean. Right? We can just go ahead and try to code that. Okay, guys, so since we're going to be doing that on an actual neural network, we'll already have a neural network implemented in our framework, right? So let's go and do that. So we have a finite diff in here. So that's basically the function that implements that finite difference thingy. It just computes the current cost, it just adjusts things and stuff like that. What I want to do, I want to introduce another one, and I'm going to call it something like backprop. Right. So the idea of this interface is actually rather simple. So here you provide the neural network and another neural network which is a gradient for this specific neural network. And then you provide the epsilon, basically the step for the finite difference, and then the batch, the training data. So this is the input training data, this is the corresponding output, and it just like computes the difference between the cost function and puts all of these differences in a gradient, right, with a certain epsilon, of course. Right. I want to implement the same kind of idea for the interface, but we're not going to provide the epsilon because this is going to be like a gradient. Right, this is going to be a gradient, and here we're going to have an input and output. So, and let's just go ahead and implement that. So essentially what I want to do is implement backpropagation for that specific neural network and put the gradient into a separate neural network. I think it's kind of like... I think it's kind of redundant. I'm pretty sure you can update the weights and biases in place, but I still kind of want to have like the gradient separately, so I can just do one step and literally print the differences. Well, I suppose I can do that if I just copy the previous state of the neural network or something like that. I don't know. I kind of like this. Maybe in the future I'm going to change this interface. Who knows? Right, so this is the finite difference, and let's just go ahead and try to implement this entire stuff. As I already said, we're going to have like a 4 nested loop, and the outer loop is all the samples, and all of the samples is just like these things, right? So this is a matrix. Each row of this matrix is the input, and each row of this matrix is the output, which means that the amount of their rows should be equal, right? So they should be the same, essentially. And we can basically assign the amount of rows in here to n, so it's like a little bit easier mentally for us to just do it like that, and we know that I is the current sample or something like that, right? So that's basically what it is. So for each sample, we basically, first thing we need to do, we need to effectively forward the current sample, right? So the current sample is actually the current row. So we can take the row, the ith row of ti, and that's the input, and we can try to copy that specific row into ti input, into the input of the neural network. So and then input, and there we go. So that kind of assumes that these things are going to be equal. Does math copy check for the sizes? Yeah, I think it checks, so I don't really have to check that myself. So we take the ith row and we put it into the input of the neural network, and then we forward this entire neural network. So, and then in the output of this neural network, we're going to have probably something, hopefully, equal to the ith row of TO, right? TI and TO stands for training input and training output, right? So we take the row of training input, we put it into the input of the neural network, we forward that will just like activate everything and just put this data through the neural network, right? And then we have an output, and we just need to see how much this output is close to whatever we expect in here, essentially. Right. And here is an interesting thing, right? So here is an interesting thing. this is how we already did the forward pass, right? So this is the forward pass. It's done by the call of this function, right? So it's already done for us. We already have all of the activations, right? Derivatives. What's cool about sigmoid is that we don't really need to have the partial derivatives computed, because we can always compute them based on these activations, right? We can always compute them based on these activations, so we don't really need that. All right, so now we need to get that difference from that imaginary layer, from that imaginary output layer, and we know that that difference is basically differences from between this thing and what's expected, right? So essentially, we want to iterate the columns of the output stuff, right? So we want to iterate the columns of the output stuff. Though we do not really check, right? We do not really check that the amount of columns of the output and amount of columns of this thing is the same. So this is probably something that we want to check. I want to do and then assert. Right. So the output amount of columns should be equal to the amount of columns in here. So this is quite important, I think, to check. So, and in here, I'm going to be just like iterating zero calls, right? So this has to be J, I'm sorry. Okay, so we take the output. All right, so we take the output and we have to, so it only has one row, so the row is going to be 0, but the column is going to be J, right? And we need to subtract what is actually expected in here. So it's going to be mat at to the row is I, because it's current sample, and the column is J, and so this is the difference. And the question is, where are we going to store that difference, right? Where are we going to store that difference? This is actually kind of interesting, right? So because in an N, we already have the activations, right? So if we take a look at an N, right, so we store the weights and biases and intermediate activations, and we have more like a count plus 1 activations than the layers, specifically because we need to store the actual output, right? So, and we can't really use that intermediate memory for the activations, but we have a duplicate of the activations in the gradient itself. Right. So essentially, I use a separate neural network. To store the gradient because I want to be able to print it and see it. But because I make a clone of the neural network, it also creates waste of memory in terms of this like activation stuff, which we can put in use. What if in NN, in the activation arrays and activation matrices, we store the actual activations after this forward, but in a gradient, we store these differences, these partial derivatives of those activations, right? So we kind of naturally have a place to store these intermediate partial derivatives, which we can do, right? And essentially we can just like go ahead and store that in the output of J, 0J, and there we go. So, and this is where we store all of that. Cool. So we pre-computed the partial derivatives of activations from that forward imaginary layer, from the next imaginary layer that doesn't exist. So now we need to start iterating the layers backwards, right? So let's do size t L. And we're gonna start, like how many layers do we have? Like we have n count, right? So, and is gonna be while L is greater than 0, minus L, right? So minus L. So there is actually a little bit more for loops in here. As I said, there will be like first samples and then layers, but there is another one for the amount of outputs in here, just to prepare this like you know, first derivatives of the activation. So that's something that is going to be needed in the future. Okay, so we need to start. So we started iterating the layers, right? We started iterating the layers, and for each layer, we need to start iterating the activations of the current layer. So how can we even do that? How can we even do that? So how many activations of the current layer do we even have? So if we take a look at the activations of the layer L, and that's the correct layer, right? So it's a row, so that means rows in this particular case is equal to 0, so there's no point in looking at that. So that means here, this is what we need to iterate. So we're iterating the current sort of activations, right? So let's actually denote them with J, because I is already taken for the samples, right? So we can say something like I current sample, L current layer, so then J current activation, and we also need the previous activation, right? Previous activation, let's denote that with K, right? So this is going to be like a 4 nested loop, ILJK, right? So something like that. So we're going to iterate from 0, J less than that, plus J. Right, and I think we can already compute something on that specific layer, right? On that specific layer, and this is basically the biases, right? So we can compute the biases because they don't have anything in here. So bias is only for the current neuron, right? So you don't have, if in case of weights, right? In case of weights, you have several weights per neuron, and that's why for a single current neuron, you need to iterate each previous one, because by iterating each previous one, you basically iterating each of the weights. For each neuron, you only have one bias. So for computing the partial derivative for the bias, you don't need to iterate through all of the previous activations. So because of that, I can actually put this stuff in here. So we're going to store the derivative in the gradient itself. So we're going to say, okay, so this is G activation. So the current activation is already taken. So actually, yeah, this can be L minus 1, right? This is the L minus 1. And inside of this thing, mat at, right, so the activations are the row, so that means row is 0, but this is J. Right, and how we are computing all that? We're computing all that by multiplying it by 2, and essentially, yeah, taking the difference from the previous one. So we can say it's something like dA. Did I do fucky wacky in here? Yes, I did a fucky wacky in here. So this is a completely incorrect stuff. So let's, yeah, I can see how it is incorrect. So because, yeah, I completely forgot the rest of the derivatives that we need to put in here. So this is just that. Well, I mean, this thing. That, yeah. So let's recompute. It's going to be in ML notes. Yeah, there we go. This is what we have to have. So for B, we only need the activations of the current layer, right? We only need the activations of the current layer. And let's take a look if we can have them. So this is going to be A and an N as L, right? So this is going to be basically that, and mat at row. So this is a row 0, and we take the J, so this is A. So we just take that, and the actual difference dA, right? I'm going to denote this scary thing with just dA because that's what it is. We're actually taking it from the gradient, which allows us to compute this kind of stuff quite easily. It's going to be dA multiplied by A 1 minus A. That's it actually for that specific thing. For that specific thing. So okay, so we managed to compute all of the biases, but this is where it becomes complicated. Now we need to compute the partial derivatives for the weights and for the previous activations so we can propagate them further, right? So we can propagate them further. And that means that we need to start iterating through all of the previous activations, right? All of the previous activations as L minus 1 actually, right? So calls plus G, something like that. So all of the previous activation. And how are we gonna be constructing all of that? How are we gonna be constructing all of that? So we need to compute sort of like the current matrix, right? If that makes any sense. So this is bias, by the way. Yeah. We were computing biases. Plus K, thank you so much. But nobody told me that I had to actually put biases in here instead of activations, of course. Everybody noticed the easiest thing, plus K, not the hard thing. Alright, so yeah, but primarily because I fucked up this thing in here, right? So the thing about the backpropagation stuff is just like it's very difficult to explain. I think the best explanation online is by 3 blue 1 brown that I'm gonna put in the description. Literally for people in the Twitch chat, you can just like go to YouTube and just do 3 blue 1 brown neural networks and you'll instantly find that playlist. And there is one of the episodes where he explains backpropagation. He actually dedicated 2 videos, 2 separate videos to backpropagation, right? So imagine like how complicated that topic is, that 3 blue 1 brown, the master of explanation of mathematical things, dedicated 2 separate videos for that, where in the first video he basically laid down the high level intuition, and in the second video he went into mathematical details, and even then he didn't went into as much details as I did in here. So in his second video where he supposedly went into mathematical details, actually he didn't even demonstrated how you write that in a code, because I suppose you're supposed to come up with that yourself, but there's still some feeling like missing. There's a lot of things that you still need to play yourself, right? And it's not very difficult topic per se. Thank you so much for posting the video to this thing, right? It's not difficult topic, it's complicated. So this is a fundamental difference. It's not difficult, it's just complicated because there is like too many layers of complexity for human brain to keep track of, right? So it is genuinely difficult for a human brain to comprehend all of that, because again, you have 4 nested loops, and it's not like you can just abstract them away. You need to think about them simultaneously. You need to think simultaneously about all 4 layers of nested loops to get the idea across. It's hard, man. It's freaking hard. And I'm still not sure that this thing is going to work. Like, I kind of know how to code that, but I'm already a little bit lost. Right. I'm already a little bit lost. I'm not sure in which order I have to pass J and K as the coordinates for the weight matrix. I just don't know. My brain cannot visualize that because I'm already keeping keep track of too many things already. It is not difficult per se, it is complicated. It's the complexity that kind of like makes it like this. But again, if you don't want to get into like details too much and understand stuff, you probably don't really have to. Right, you probably don't even have to, because all of the neural network frameworks just do all of that for you. Like, why would you need to understand that? But I personally kind of want to understand that. I was always this kind of guy that it's kind of difficult for me to use something. Like, it's difficult for me to use black boxes, right? it's difficult for me to use black boxes because I like to go inside of the black boxes and like really rearrange them. Right. So it's kind of difficult to explain why like going inside of the black boxes is so powerful. So imagine that you have two black boxes and you need to kind of solve a very specific problem that is kind of difficult to solve when you're thinking about them on this level. It's kind of like none of the black boxes sort of fit together, right? They kind of like you put like inputs and outputs together and it's never kind of fit, and you have to put like additional hacks, more black boxes to actually feed it across. But quite often, if you look inside of the black boxes, right, if you look inside of the black boxes, whatever you combine as inside of two black boxes might be the right solution that you want. I know that I'm just hand waving, but that's how it feels for me when I go inside of these black boxes, right? Because quite often you can't really solve the problem on this level. It's kind of like difficult. But if you break it down, if you go a little bit deeper, you can rearrange some of the stuff from insides of these black boxes and get exactly what you want. You know what I mean? So, you know what I mean? It's kind of like difficult to explain, and I can't really provide like exact example. But this kind of shit happens to me way too often when I was learning how things work inside. All right. So, because like when you see only like high-level black boxes, you don't really see a lot of things that could help you to solve the problem efficiently. Right. If that makes any sense. That's why I kind of like to look inside and see what parts of the inside of the black boxes could be rearranged from the inside of different black boxes to get a new black box that didn't exist before. You can't create a new black box that didn't exist before if you don't look inside of other black boxes and see how their insides can be combined together. Right. Many refer to this as thinking from the first principle. I think I heard that phrase from Jonathan Blow quite a lot. Is that what he means when he says first principle? Because he keeps saying that thing and I'm not quite sure what exactly he means by that. Right, it's probably that. So... but so what's interesting, like I used to program on a very high level, right? So I used to work as a Java enterprise developer, but the more I start digging inside of these black boxes and realizing how you can rearrange their insides and get more interesting emergent and synergetic behaviors, the more it became addictive to me, if that makes any sense. It is kind of addictive how you disassemble these black boxes and you just unlock something that was not visible before. It's extremely addictive that you can't stop. You keep like digging down and down and down. What else can I discover in there? It's just like fucking insane. Yeah, it's just like keep digging down and down and you discover more and more. You rearrange things and it's just like holy fucking shit. And all of that power was hidden from me all the time. I couldn't see that. All right. So, and like what kind of shit I can discover if I go down like below hardware level or something like that? I don't fucking know. So it's insane. Anyway, it's kind of interesting. And that's why I spent 3 days making sense of this shit. Right. So anyway, so what I was doing, we are iterating all of the current layers, right? We're iterating all of the current layers, and for each current, all of the current activations, and for each current activation, we're iterating each previous activation. Right. So here's the thing. So let's imagine that we have the current activation, and the thing is, my framework basically passes rows through the network. Right. So if you have something like this, right? So this is the row, and then you have a bunch of vectors, right? So here you would, for instance, say, right. So here you have 3 activations, and let's pass them through two neurons, right? And it's going to be something like this, right? Yes. So this is something like this, and that basically creates two new activations in here, right? So the reason why I do it like that is because it's kind of easy for me to think about matrix multiplication as just basically this intersection, right? So this activation is computed on intersection here and here, right? And then I pass it to the next activation in here, right? So and so on and so forth, basically, right? You see what I mean? So here is going to be another like this, and we'll basically expand it to 3, but maybe it has to be, yeah, so it's going to be like that, and so on and so forth. As far as now, this is not particularly conventional in neural networks, right? Usually you pass activations as a column, right? You pass activation as a column, and you multiply from a different side, right? So essentially I have 1 by 3, and because of that I have a 3 by 3, or like 3 by 2 in here. So this is 3 by 1, right? So that means the weight goes to the left, right? So I suppose the actual convention is something like this, right? And maybe because it just looks nicer, because you write it like that. I don't know the actual reason, right? Maybe it just looks nicer. But in my framework, I did it like that because I don't know any better, right? Maybe in the future, we'll have to change it to a different convention. But for now, I kind of stuck with this sort of convention, and I'm gonna just go with it, if you know what I mean. Anyway, so essentially, this is the previous activations, right? We can think about that stuff as previous activations. And this is the current activation, right? So this is the current activation. So that means the current activation, right. Wait a second, why? Okay. So current activation is the weight matrix column, right? So if this thing is the current activation that we supposed to compute, and the current activation is J, that means the J is the column. So that means K is the row. Weight matrix row. It's kind of important, right? Because you can actually quite easily get lost while trying to understand and compute all of that. It's kind of like, yeah. All right, so what do we do in here? So we need to do GWS L-1, and the row is K, right? The row is K, but the column is J, right? Something like this. And what we add in here is 2 multiplied by dA multiplied by A, 1 minus A, as usual. And then we need to take xi, which is activation. Well, it's supposed to be activation of the current layer, but I just left it as xi. So, which is another mistake in here, right? Is it activation of xi? I don't think so. So let me see. So this is going to be the weight. Yeah, it's activation from the previous layer. So it has to be activation I L-1. All right. So we can probably do PA, which is activation from the previous layer. And so this is going to be matrix at row column multiplied by PA. Hopefully I didn't make any mistakes in here. Right. So we already managed to compute to like a partial derivative for the biases and for the weights, and this is 2/3 of the way. So now we need to compute the activations, you know, differences for the activations, and they're going to be computed into AS, but I suppose L minus 1, yeah, that makes sense. So it's gonna be 2. This one also has to be a difference. Okay. I keep finding errors in this entire thing as I implement this entire stuff, which is kind of funny. Right, so yeah. Yeah, so that makes sense. So dA, A minus A, and we have to take the weight, right? And I suppose the weight is going to be one of those things, right? So float weight, but we take it from NN. So I'm not sure if all of that is going to work at all, and I'm really curious, but yeah, we're about to find out. So yeah, there we go. So basically computed all of the intermediate derivative and stuff like that, but they are not divided by n. So after we computed all of that for the entire thing, we need to iterate through all of them and divide by n. Right, so let's iterate through, well, I mean, we have separately weights and biases, so we have to do something like size less than I, right, G, W, S. We iterate in the rows of this entire thing, so this is going to be I. Well, we need to iterate the count. Yeah, for each layer, right? So it's going to be n G count. So this is just the layer, then size J0, G W S I. Rows plus G, and then columns. Then we take what we have in here. It has to be K. It has to be K. JK divided by n. Right. So, and then we have to iterate through all of the biases in here. Right. So it can be S. Yes. And that's basically back propagation. So Matt at WS, yeah, I see what you mean. Just a second, I will zoom in on your comments. WL, but informally you have L. This one is a little bit complicated, right? This one is a little bit complicated because this is the specifics of our indexing in our framework, right? So we have count layers, right? So if we take a look at the definition, this is a very good question, by the way, right? So because it could be a source of confusion like that. So here's the count, right? Here's the count. And this is the amount of layers of neural network, right? And we have 3 arrays of matrices: the array of weights for the current layer, the array of biases for the current layer, and the array of activations. And the amount of activations is +1. The reason is, right, so you have layer, first layer, right? So then the second layer, maybe we can do VB1. So WB stands for weights and biases, right, and so on and so forth. So maybe we can even do that from 0. Right. And since we're programming in C, right? Since we're programming in C, we pre-allocate all of the necessary memory at once, right? So, and essentially, input is A0, right? So A0. And by combining A0 and VB0, we get A1. By combining A1 and VB1, we get A2 until we get, right, so here we have WN, but here we have A, like N, like this one is -1, right, this -1. So there's more activations than 1. So that means the current, and we are actually iterating not from count -1, we iterating from like +1. We currently, L is currently pointing on the layer after the current one. So it's, you see, it's kind of like, yeah, so the framework itself adds a little bit more complexity into the index chasing, right? index chasing. All right, so, and yeah, that's basically the reason. So if we had like a more higher level language, maybe it would not be a problem, right? But yeah, you get, okay. Thank you. I'm really glad that I managed to explain that. Okay, so let me go through everything just to make sure that I didn't do any fucky-wucky and potentially any oopsie-doopsie. So our convention with for loops in here is that I is the current sample, we're iterating through current samples, then L is the current layer, J is the current activation, right, the current activation, and K is the previous activation. Iterating through all of the samples, so copying the sample into the input of the neural network and forwarding it. Okay, so that means in the output of this thing we got some stuff. We're iterating through all of the columns of the output, right? So we take each individual value of that output and then the corresponding value from the expected output, we take the difference and we put them into the output activation of J, of the gradient, because we use it as an intermediate thing. Right, so, all right, we're starting to iterate the layers from the last one up until 0, and we ignore the 0, and the reason why we ignore the 0 is because we sometimes get back, we do L-1, and you cannot look past 0, so that's why we do it like that. So for the current layer, we look through current activations, and the current activations, it's basically L. Their columns, we look through the columns. Okay, that makes sense. So we came to the conclusion, right, so that maybe I actually have to put it in here because this information is kind of irrelevant until you get to this particular part. Okay, so I take the activation, the current activation, we're taking it from the neural network itself, right? So that's what we're getting here. It's a row, so that's why it's 0, and we take the J column. So, and then we also take the difference of the activation, basically the derivative, right? It's the derivative of the activation, and it's coming from the J. For the very first layer, it's going to be literally the difference that we computed from the sample stuff, right? So, and then we computing the derivative for the biases for the current layer, and for this, for the weights matrix and for the bias matrices, the current layer is L-1, right? Because it's kind of shifted because of the indexing and stuff like that. So let me double check. So for the B, essentially we just take 2 dA, A, multiply here, but I mean the compiler would have told me this specific error, so that should be fine. Okay, that's fine. Cool. So this is the only thing that could be computed on that level, on the third layer. The rest of the stuff has to be computed in the innermost loop because it involves the previous activations. So that's kind of important. Okay, we are iterating through the previous activations, right? So iterating through the previous activations, and the previous activation is, yeah, basically one of those. So we keep track of that. So I'm still not sure about this statement. I need to double check that specific statement, that the J is the weight matrix column, right? Because, okay, so this is how we multiply. So the current activation is J, right? So that's the current activation. So that means it's a column for this thing. Right, so where is this thing? Current activation is J, and it's a column, so that means the J is the column, right? And row is one of the previous activations, so that means it's a row, so that should be fine. So for the previous activation is K, for the current matrix is KJ, right, because it's a row and column, right? That's how we index them, right? And this is from an M. So for the gradient of that current thing, we say Kj is equal to that and this specific previous activation, right? This specific previous activation. Okay, and for this thing, we just use the matrix. Looks good to me. Which is good, looks good to me. So that should work, I think. I think that should work. But I'm not 100% sure. Not 100% sure. A little bit scared. A little bit scared, but let us see. Right, so let's try to recompile Zor. Right, let's do Zor. Calling all zor.c lm, and let's go to the compilation errors. Right, so so this is multiplication. So these compilation errors are really easy to catch. Okay, so this one is very important. So we're iterating through the previous things. So this is a row, so that means we have to do something like k in here. Right, and this one is very interesting. So yeah, because how neural network works. Yeah, this one is really interesting. So imagine that we're iterating through the current layers, and then iterating through each individual previous layer. So change in this, in the neuron of activation of this one affects this neuron, but it also affects this one. Right. So essentially you kind of have two separate derivatives. Change of this over this, and change of this over this. Which one do you pick? Which derivative do you pick for that specific error? Which one do you pick for that specific error? This is a good question. And I watched the 3 Blue 1 Brown explanation, the second video on backpropagation, and the only thing he said about this specific situation, he literally like said 1 or 2 sentences of this specific situation. He said, just sum them up. Like literally, he like this is a very like interesting situation. Like it's like, what the fuck do you do with that? And he's just like, yeah, just sum them up. Right, and didn't really go much into the detail. And it's just like, do you really sum them up? Do you have to take the average of their sum? Why not average of the sum? Maybe average of their sum would make sense. Why just sum them up? I don't freaking know, but yeah. So maybe there is like a reason if I went deeper. Right, one of the things I could probably try to verify is just like try to compute the derivative of the entire neural network without backpropagation. Just like basically tank the complexity, right? Of course, when you start doing that and apply chain rule, it's just gonna explode with complexity, right? But just like tank this complexity and see if you ended up with the same solution as with backpropagation. Right, and that's how you can confirm that, but I don't want to do that. Like, I definitely don't want to tank computing the derivative of the cost function without backpropagation. Like I don't want to do that because it's just like it will just basically explode. The more nested layers you have, the more it's going to explode basically. Right. Yes, you sum them up. It's like a partial derivation of transformation from xy to r theta. Doesn't really make much sense to me because I'm not a mathematician, but I will just trust you since you're a mathematician. Right, and 3 Blue 1 Brown also a mathematician, and it's just like 2 mathematicians told me that I have to sum them up. So that means it's probably true, but I'm an engineer, so I don't check things. I check things by just running them, and if they don't catch fire, it's good enough for me. Right? I know it sounds weird after 3 hours of this shit, but I'm just an engineer, I'm not a mathematician. Anyway, anyways, so everything seems to be working. So let's actually, let's actually go ahead and see if it's going to work. The fun will start if this won't work the first try. It's gonna be unbearable. Anyway, so let us see. So what I want to do, I probably want to just comment this stuff out, right? And I'm gonna just do that. Okay, if we just run Zor, what happened in here? So we got the actual neural network. Maybe I'm not gonna print the actual neural network. I want to print the gradient that we computed using finite difference, right? So let's actually fixate the random number generator. Yes, well, I mean, I probably have to recompile this. I'm sorry for saying that word again. this is finite difference, right? So this is finite difference. And now I'm gonna quickly switch this finite difference to a back prop, right? So finite difference uses epsilon, so let's actually put this epsilon in here. So else, right, else back prop, back prop. So and if. Okay, the moment of truth. So it doesn't really accept epsilon, right? Okay. Not bad. At least we don't see nans in infs. That's already good, right? So that's already freaking good. So if I comment it out, this entire thing is supposed to be... Okay, so this one is a little bit dangerous, right? So I forgot a very important thing, I think. I forgot a very important thing. We need to clean up the entire gradient in here. So right, I would like to do something like and then 0, and I want to fill up the entire gradient with 0 before doing all of these accumulations and stuff like that, if that makes any sense. Right. So, and I don't remember, so does it, we don't have such function yet. Okay, so we have kind of like copy. Right, we don't really have copy. No, I don't have copy. Okay, so let's do and then 0, and here we're going to accept the neural network, and we're gonna just like fill it with 0. So let's put it in here. So we're gonna iterate through all of the layers. Right, less than and then count. Actually, count, please. So this is the layers, and for each of them, do we have mat 0? We don't have a mat 0? Ah, I think we have a mat field. I should have actually called it an NN field then. Whatever. So let's do mat field. WSI, just fill it with 0, BS and AS as well, but in case of AS, you also have an N count, right? So there's an extra layer to fill with 0. So back prop, back propagation. Right, so and I think there is another interesting thing in here, right? So we filled all of that stuff with 0. We filled all of that stuff with 0. And in case of the gradient, we compute intermediate like DAs. We compute intermediate DAs. Compute intermediate DAs for each sample. So I suppose for each kind of layer, what we want to do, we want to clean up this A's, right? So because here, for instance, we just set G, but we can have the values from here. So I suppose we want to just like set 0 on each individual layer in here. I guess that's what we want. So let's quickly do that. So I want to do J from 0 to equal actually, and then count, right? And JAS J mat fill with 0, right? So this activation, I think it's kind of important because they carry a lot of intermediate stuff that is not important between the samples. So this is quite important to consider, I think. Right, so okay, so here I actually disable this thing, so let me enable the back propagation back. And yeah, this is the reason why I wanted to do that. So because in a finite difference, if we switch to finite difference, I remember that those weights were negative. But then when I switched to back prop, they became positive, and this is actually very sus. And if we don't clean this stuff up, if we just literally remove this entire thing, they become positive, and this is a completely different gradient, and this could be a disaster. Right, so yeah, actually I'm really glad that we caught that really early. Right, so and this is one of the reasons why I want to be able to print those you know, the gradients, just to see them, right? And they're kind of similar, right? They're kind of similar, but they're different, right? So the different, I feel like the gradient is a little bit bigger, right? Because it could be a little bit more precise on how sensitive the parameters are in to the cost function, right? And it can tell you precisely how to move in a certain direction. Okay, so we can try to learn from a single sample, right? So we're currently at back propagation, and let's see how a single sample improves. Does that improve the cost function? I think it does. We had 9 in here, now it's 8. So what I found with back propagation, you can even have like 1, and it's gonna be fine. It's gonna actually learn relatively fast. Right, so it was 9, it became 5. So now we can try to maybe train for 100 epochs, and it kind of goes down, right? As you can see, kind of goes down, which is nice. And it's, yeah. So with just thousands of iterations, it's, well, it's not bad. But this is because we made a faster rate. What if with this rate I'm gonna do finite difference? It's also nice. Okay, so this is because of the rate. Well, yeah. All right, so we implemented backprop. We literally just implemented backprop. So what about 5 in here? Yep, that's cool. So this is a backpropagation. To be fair, it would be kind of nice to see if backpropagation actually saves time. Backprop first try, yeah, that's exactly. So let me quickly commit the backprop. Unfortunately, my sort of like tour through the forest of the backpropagation partial derivatives is not a particularly great explanation on how it works, and I really apologize for anyone who's going to watch this entire stuff. Right, so a better explanation could be, like, again, as I already said, is done by 3 Blue 1 Brown, right? But even his explanation is like requires you to stop and ponder, if you know what I mean. Right, so, but here we have something. I'm not sure if there are any mistakes in here, right? So, because this is a very like complicated thing, it's just like 4 nested loops. And it's not like you can put some of the loops into separate function, forget about them. You need to sort of like mentally keep track of all of that. And on top of that, we're using a convention, like unconventional, you know, indexing of the matrices. So, yeah. Anyway, so what I want to do is I want to do a committee, right? So I'm going to literally just make a commit and say implement and then backprop, right? Implement and then backprop. I'm going to push that right into the repo. If you're interested where you can find the repo, where is my browser? The repo is located in here, right? So, and the PDF is going to be available in here in ML notes in a separate repo. It was complex, but I appreciated it. The only annoyance is that there is no way for me to pay you. You don't owe me anything. You don't owe me anything. Don't worry about it. So, but again, so for just learning a little bit about neural networks, right? Just in even training simple neural networks, you don't need a backpropagation. You can just use finite difference, right? And finite difference is just like basically wiggle one of the parameters of the model and compute its cost, subtract the original cost and divide by that small wiggle, and you kind of get the direction in which the function wants to go, and you subtract that direction, go in the opposite direction, right? So you can approximate the gradient. Gradient is being basically very precise about like how you move and stuff like that. But you don't really have to be this precise. But I wanted to be this precise just to learn how it's done and stuff like that. Right. So this is actually kind of cool. Okay. So let's try to do a random stuff. So I want to migrate completely to backpropagation here, so we don't really need epsilon anymore, right? We don't really need epsilon. So, and in here then we just print the final thing. So in here we have like only 5,000 things, and it's enough to just train this entire thing. And here are the weights and biases of the neural network. Weights and biases that implement Zora. So as far as I understand, gradient is more effective when you have huge networks. In such small NNs, it's not much better than FD. Yeah, maybe we need to build a bigger network. Let's actually give it a try. So we have a XOR, right? But what if we try to build a summer or adder? Yeah, let's call it an adder. So let me try to do that. Adder.c. Right, so we're gonna have a full adder, right? And a full adder, let's create some like training data for the full adder. So it's gonna be float training data. So this is a training data. So let's say that the full adder actually has 3 inputs, like the first bit, the second bit. Well, I mean, it's not necessarily something like that. So let me think. So I want to implement the following adder. Right. So I want to have like 2 bits in here. Right, then 2 bits in here, some sort of like a black box in here. I don't know how many layers we'll have in there, and then 2 bits in here and another one in here. Right, so essentially we have something like this. Right, it's fully connected, of course, and here we have something like that, and then this is the last one. So essentially you pass your first number A into these 2 bits in some representation. Oh, I don't know why I removed that. And the second number in here, and you get the third number, which is the sum of these 2 numbers, right? And this one is the carry bit, right? So this is the carry. So if, or maybe we can call it overflow, right? So it's an overflow. Let's call it OF. Oof. Right. So yeah, it's an overflow bit. If basically the sum overflows, these things are going to be 0, right? And this one is going to be set to 1, right? Something like that. So, and here's an interesting thing. I want this thing to be a variable in the sense that I want to have a global parameter n, which for this specific neural network is equal to 2, right? If I set it to 3, I want it to automatically scale to 3 in here and 3 in here, right? And I want to just like keep increasing the amount of bits that you can compute, right? And see at which point the difference in performance between finite differences and back propagation starts to matter, if that makes any sense. Sounds good? Sounds good? Sounds good? I think it does. All right, so let's go. Let's fucking go. In this case, you could generate the training set. Also works with, yeah. I mean, of course, like, yeah, I'm specifically picking the examples where I can generate the training set, so I don't have to worry about this kind of stuff. I have actually a lot of different interesting ideas where the training set could be just generated, right? So this is ideas for the future streams, right? This is ideas for the future streams. Okay. So let's introduce the thing called bits, right? And initially we're gonna have like 2, right? So this is 2. So in here I'm gonna just include nn.h, and we have to define nn implementation. All right. So what we need to do first, we need to generate the training data. So this one is gonna be input, right? So let's allocate the matrix. So how many samples are you going to have? Right, so how many 2-bit numbers do you have? You have this amount of numbers. So, and how many additions between them? So how many combinations of them you can have? Basically, multiplied by that, effectively. And that's how many rows we can have. Right, maybe we can even do something like rows. And this is the rows. And so this is the rows, this is the amount of things. But in terms of like input, how many inputs can we have? We can have 2 bits, right? Because it's a bits plus bits, right? It's a bit plus bits, it's a 2 bits. Okay, so that's fine. We can even try to generate this entire stuff. So if we iterate through the rows, rows plus I, so then we take a row. Right, we have to iterate the columns. So maybe we can even do something like ti rows, and then we're gonna iterate the columns. Size t j0 j ti calls. plus j. Though this is not how we want to generate that for sure. This is not how we want to generate that. Essentially, we want to actually generate it something like this, right? So we're going to have x, which is less than one of these things, which we may want to extract to something like n, right? Something like n, so it's a little bit easier for us to work with. Right, so then size t y0 yn plus y, right, something like this. And that doesn't tell us the row, the actual row in here, so that means we have to compute that row. We can say that that row is sort of like index one of them. It's x multiplied by that specific n plus y, right? So we can consider it like a square, right? So it's sort of like a square. Sort of like a square. Or maybe, what if I invert this entire stuff? Yeah, what if I invert this entire stuff? Essentially, what if I iterate all of the rows to I rows, and then from them I'm computing x and y. Essentially, x is going to be equal to I divided by n, so this is x, and y is a mod n. And then I'm going to be iterating j, which is the columns, which is not necessarily columns, but it's actually bits. Alright, so this is bits. And then what I can do, it's a mat at ti, the current row is I, and then I just iterate the current bit, and the current bit is equal to just basically that, like this. But then for this thing, it's multiplied by bits. Good enough. Furthermore, I can do a lot of interesting things in here. So I can, yeah, let's actually keep it like that for now, right? Let's keep it like that. That should be enough. So that should generate like all of the possible combinations and stuff like that. This one has to be y, by the way. So, and then I'm going to do mat print ti. Okay, so let's do adder. Does it work? I think it worked. Yeah, so it did that in a different order in here. That's a really strange order, isn't it? Yeah. Now that's better. Okay. Yeah, so that makes sense. That makes a lot of sense. Yo, yeah. So I'm already a little bit tired, so I really apologize for very stupid fucking mistakes, man. Right. Stupid fucking mistakes, man. Okay, so let's actually create outputs, right? So it's a lock rows, but output is going to be the amount of bits plus the carry bits, so 1. Here what we can do z, which is essentially x plus y, right? It's essentially x plus y. And essentially, it will very much depend on what exactly we're doing. Right, so if z is less than the maximum value, that means we just do that. And we can quite easily even do something like to row I j equal to z j1. All right, but otherwise both of these things, like all of these things, has to be set to 0. And I will hope that the compiler will just invert the loops. It will just generate 2 separate loops in here, so it doesn't really do this kind of stuff. Right. So the compilers can actually like put fors and ifs inside out, So you don't have to do this comparison on each iteration, so you can have two separate loops. So that's why I don't really care about that. Right, and here we can do one of the interesting things. Essentially, mat at 2, right, mat at 2, I beats, right, because we have beats plus 1 in here, right, we have beats plus 1, and we can literally set this thing like that. If it's less, if it's not overflow, otherwise blah blah blah. And then we can kind of reuse this entire logic like here. Maybe we can say, all right, overflow. So to increase the readability, if you know what I mean. So this is overflow. If overflow, we just set everything to 0, otherwise we just kind of, and this one is overflow. Does that make sense? I think it makes sense. So let's just print on that. Okay, so there's different sums. This doesn't make sense. I feel like I fucked up something badly. Why input 0 if it's overflow? I think it makes sense. Oh yeah, I'm an idiot, I'm sorry. You're right. So again, I'm super tired right now. So super tired, extremely tired. Yeah, okay, so that makes sense now. Thank you. All right. Okay, so this is basically the training data. Cool. So let's create a neural network that will accommodate all of that. So we can try basically the following architecture, right? So we're gonna accept 2 bits, right? 2 bits, and then so this has to be like this, and the output is going to be bits plus 1. So we're not going to have any hidden layers for now, and let's allocate this entire stuff. And let's see if it's going to work. So I also want to take a look at this entire network. Right, so what do we have? Yeah, we have to swap this stuff around. I don't remember the order of the arguments in here. From 0 to 1. There we go. So that's the neural network we have. Right. So this is the 4 inputs, then 3 outputs. Yeah, it's actually, yeah. So the rows are the inputs and this is the outputs. So that's the entire thing. We can compute the cost of this neural network with respect to TI/TO, just to see how it goes. All right, so we can say this is the cost, because we want to be able to see that. I think it's kind of important. That's the entire cost. Cool. So let's compute the gradient backprop, and then GTI/TO. Let's take a look at the backprop first of all. So does it make sense? It kind of does make sense. It actually grows. Okay. So and then learn, and then G rate. I think that's it. We don't really have to provide TI/TO. I'm pretty sure. Float rate. Let's set it to 1 for now, and let's take a look at if that improved the gradient. It freaking did. Let's fucking go. Let's fucking go. Okay, so it's going down. It's going down. So what about 1,000 of those things? Look at that. It's stuck at 46. That is interesting. Okay. Let's go to nn.h. Overflow is wrongly computed. No. Okay. So that means we don't have enough hidden layers. So let's actually try to maybe add, as far as you can see, y. If n, this is the maximum value, right? So this is the maximum value that we can have, which is 2, right? So which is like 4, right? So if the sum of these things greater or equal than 4, that means it's an overflow for that neural network. Okay, so the amount of this thing, so this is n, this is how many numbers you can have on one side. All right, so so it's actually maximum that you can. Oh, I'm really need to make a small break. Like, okay, we're making a break. Okay, I was gaslighted, so everything is fine actually. So let's not listen to the chat anymore. Okay, so yeah, so essentially what I want to do, I want to add a little bit of the bits to the inner layer, right? So how many like inner things can we add in there? We can add 1 bit in there and see if it's going to improve. Okay, so it's actually went lower, 46, which is nice. Can we go even lower by like increasing the amount of iterations? I don't think so. Nah. Well, I mean, it's kind of going somewhere. So I would presume that you kind of maybe need the bits amount of additional things to go anywhere. And okay, it's going somewhere. All right. So what if we just add another one just in case? And that was actually very effective, I think. It's actually kind of cool. Okay, so let's actually switch to here, right? So because it's a little bit faster. Right? Was it right? And I'm gonna increase the amount of iterations in here, right? So I'm gonna increase the amount of iterations like twice as many. Don't run, please. Don't run it. Just recompile because I'm gonna be running it in here. And doesn't really go much lower than that. What about 100? So maybe yeah, so it kind of stops at there. Maybe we want to add as many bits in here as like here, so maybe that will be helpful. Right, so I'm just like literally guessing. So at least it goes below. Will it go even further? Probably not. Maybe there is some problem with the overflow. Maybe there is. It's an interesting question. But what if we preserve sort of the original bits? What if we preserve the original bits and we just like say, okay, if the final thing is just like bigger, then on top of that it's also overflows. Right, is that a good idea? Could be. So, alright, that was a good idea. So maybe it couldn't find like a circuitry for that specific behavior. That could be the thing. It's just like a very specific, difficult behavior to achieve. It actually then dropped really fast at some point. I should probably not overfit it this much, though it's a model that is meant to be overfit anyway. Right, so it's meant to be overfit. So this is actually a pretty good thing. So it's kind of interesting that sometimes that when you find the correct like architecture for the neural network, it sort of like clicks in place and the cost goes to 0 very, very quickly. But sometimes if the architecture cannot accommodate that, it gets stuck somewhere. It's just like it cannot find the combinations, like cannot brute force the circuitry. But if you get the amount of neurons and layers right, it's just like clicks in place and it just like solves. It's so fucking cool. It's kind of magical in a sense, right? So it's just like you didn't solve the puzzle yet, and then it solves the puzzle and it's just like it works. It's so cool. So what if we can reduce the amount of bits? What if we just like use this one? Is it going to work? Was it because of the circuitry? Maybe. Nah, not enough. The amount of bits in here, it doesn't seem to be enough, right? Because it just slows down. But maybe it's because it just started now. But if we add one additional bit, maybe that's what does the magic. Okay. So probably twice as many bits in here, right? I'm literally guessing, like this is how we're supposed to do machine learning, I suppose. Yeah, like twice as many bits. And plus one, just in case. Okay, so let's actually set 50,000, right? And now time to have a pool of random architectures and then augment them based on performance with random mutations also. Yeah, so we can basically raise the level of abstractions. Right, okay. So let's try to do all of that, right? So let's iterate size x 0 less than n, right? So this is going to be x. So we're going to be verifying this entire stuff. And y, and let's just print. Let's just print zu plus zu, so x and y. So let's do maybe 5,000, so it doesn't really go for too long. Right, so this is the different combinations. Right, this is the different combinations, and I want to basically put all of that stuff into the inputs of the neural network first. All right. So, but here instead of that stuff, we're going to be doing nn input of nn. All right. So we're just like feeding that stuff into the neural network, and then we do forward of nn, and this one is going to be super interesting, right? So we're going to be iterating through the bits of this stuff. We can do size t z, initially 0. All right, and then output. All right, and then output mat at row is 0. We're iterating j, and we can say, okay, if it's greater than half, that's what we're going to consider like bit. Right, so we're gonna call it bit. There we go. Greater than half, and that bit, right? Since we're compressing that bit in there, so that means we'll have to move that bit by j, right? And do something like this. I think that could be a good case. All right. So this is how we're gonna be verifying this entire stuff. First, we're going to be verifying all of that visually. Undeclared I. So this one is going to be 0 because it's an input. Okay. Is it correct? No, it is not correct even because it didn't train fully, I think. Well, like here it worked. Here it worked. Here it didn't work for sure. Didn't work for sure. Right, so let's actually keep training this entire stuff. Excuse me. Right, so we need to increase the amount of iterations. Let's do 100,000. So 3 plus 1 has to be, yeah, so we have to be super careful with that. Thank you so much. Essentially, what we have to do, let's move this stuff maybe somewhere here. Alright, so this is gonna be just it. And then if and then output and then mat at 0 bits greater than half. That means it's overflow, so what we want to print instead, overflow. Right. Otherwise, we want to print 0, 0. There we go. So that's a good one. Well, I mean, yeah, so I suppose this is a full set of training on 100. So this is going to be very, very good. Looks good to me. So yeah, this neural network behaves like an adder. It does behave like an adder. We can now add essentially more bits in here. We can add 3 bits, right? And the backpropagation seemed to be finding the solution for all of that. Okay, so I think maybe 10k should be enough, right? So because I don't really want to wait all day. All right, let's do 10k, and if it doesn't do in 10k, well, I mean, it's not worth it. Okay, so one of the things we could have probably tried is essentially, yeah, it works. We don't really want to output all of that in here. We want to just basically say okay. All right, and if we find any of the examples that that basically don't fit, we want to print them, right? Why not have loop until cost is close to 0 or less than 0? Because I don't really know for how long it's going to go, right? So I want to have like a control over how much time we'll spend on that. So essentially, what I want to do, all right. So if it's overflow, we want to do the following thing. So this is Z, like maybe we can call it A for an activation, right, for an activation, and then we can have an actual Z, which is x plus y, right, x plus y. So if we overflow, right, if we overflow, how do we compare overflow? I just want to double check. Z equal or greater or equal than n. If Z equal greater than n, actually if Z is less than n, we have to print something, right? Print. So we can say maybe expected overflow, right? But got something else. We can print that Z. So maybe we can even count the fails. Fails 0. And then in here, if Z not equal A, we may want to do something like this. Expected this, but got A. Maybe we can do something like this difference. If fails equals 0, printf okay. I think that's a good solution. This is not what I want to run adding. Okay. So if we actually train it for less, this is actually very good, you know, verification. What if we train it like for 10? Right. And it basically tells you that it doesn't freaking know. It doesn't really work at all, so it's completely failed. We can even yeah, let's actually put it like this. That's fine. So we need more. I wonder how many, like, is 1,000 enough? No, 1,000 not enough, but it's actually less, right? So it's actually less. 5,000? Is 5,000 enough? Maybe 5,000 is more than enough to actually get it. Yeah, only one, okay. What about then 10? So I think 10 is like a magical number in here. So with 10, it's gonna be fine. Okay, it's okay. Cool. So let's actually see, like, what if we used finite differences instead? Right, if 0, it's gonna be that. So would it perform similarly? Finite differences at epsilon is gonna be, let's say, 1 minus this, and then if. That's slower. That's already slower. Can you feel that? Man. So that's why people use gradient descent. It's way slower. We can actually try to increase the amount of bits. What if we increase the amount of bits, like 4? This is the finite differences. Though at some point it actually starts to go a bit faster, but man, that sucks. That freaking sucks. This is finite differences. So to see the actual benefit, we had to like compare them like on bigger neural networks. And now let's switch to backpropagation. So backpropagation also has its limits, but it's way faster. Look at that. Holy fuck. So as far as I know, backpropagation, like at the time when people like finally figured it out, it was a huge boost to like to training neural networks, right? Because you finally could do it way faster than people used to do it before, right? So, and there are other techniques that we can apply. Look at that. It's actually struggling. It's actually not enough. I wonder if it's just like started from a wrong place. I wonder from which place it started. Do we randomize anything? We don't even randomize anything. Let's do srand time. Maybe we just have to start from a different place. Yeah. Okay, so this is a different place. Or maybe just circuitry is not enough for this thing to work properly. Is it going lower? Is this open source? Of course. Use the today command and it will give you the link too. Okay, I don't think it will get it quite there. Though one of the things we can try to do, we can stack more layers, right, to make it a little bit more flexible. And at some point, yeah, so it still couldn't train on these examples. Expected 14, but actually 10. But it's like, it's close. It's close because this is like way more examples than usual. So it couldn't quite get the circuitry right. So what if we do a little bit deeper? What if we just like make it like this? Is it going to be better? So it's probably going to be also slower. Nah, it's just like really struggling with this thing. By the way, for these neural networks, for deeper, I think you have to be a little bit slower when you do that. Right. I remember having some sort of problems in that part, but it's, yeah. Yeah. So maybe the depth is not gonna solve anything in here. One of the things we can try to do, but you don't really want to make it too big because essentially what it will do, it will memorize. But in case of like overfitting model, maybe that's precisely what you want anyway. By the way, let's let's put the rate back to 1. There is another interesting technique to speed this entire stuff up. There is also a thing called stochastic gradient descent. But I wanna do this thing in a different stream. Maybe it can print, maybe, but I mean, it was doing fine with less amount of bits. Like here it goes well, kind of well. So if I just use 4 of these bits, it basically, yeah, it basically memorizes everything, I presume, right? We're almost there, by the way. Batch learning, yeah, so batch learning can actually help. So we're almost there. 10K. And I think it's gonna be okay. So because at that precision, I think it's already done. Yeah, it's okay. So we can, yeah, we can try the following thing. Yeah, if the cost gets like below 100th, right, so we can probably stop all of that, but that's besides the point already. So there is a very interesting technique that can speed up the learning quite a bit. So essentially, you have some data, right? So you have the training data. And the cost function, as you can see, when we're computing cost function, to print this entire thing, we provide the entire data in here. So the whole data, training data, is put into the cost function to compute the full cost function. So, and which could be actually like computationally heavy. So the idea is essentially split the entire training data into like these small batches, and also to make the stochastic part of gradient descent just like shuffle them around, right? Just shuffle them around. And essentially on each step, instead of using the full data, use that single batch. Then the next batch. Then the next batch. Then the next batch. And just circle through them. Just circle through them. The question is, why the fuck that would work, right? So imagine that you have like multivariable cost function. Where is that? Okay, so essentially you have 2 parameters, right? So obviously you're gonna have more parameters, but yeah. So this is gonna be, let's say, weight, and this is the bias or something. And let's say that the local minimum is somewhere here, and we started somewhere here, and there is like a sort of like a contour lines, right? So the contour lines are going like that, something, something. The gradient, actually, since it's a minimum, the gradient goes outwards, right? So the gradient goes outwards in here. So this is the vector field, right? And essentially, a gradient descent is going to be going slowly in here, right? So if you use the full data, the gradient descent is going to slowly descend in here in an opposite direction of as the gradient, right? Because we subtracted the gradient. So let's actually say that this is the thing. For a single batch, a single step is not going to be in that direction. So let's actually make it even more visible, something like this, right? So if you use full data, this is the single step. But if you use one batch, a single step is going to be here. It's going to go in an opposite, completely different direction. But here's an interesting thing. If you do basically scroll through all of the batches, your path of the gradient descent is going to look like this. On average, it's going to converge towards the local minimum. But since each step requires less data, it's computationally less expensive. So this is called stochastic gradient descent, or like batch training or something like that. Somebody called it batch training because you split the data into these batches and stuff like that. So this is one of the ideas people use to speed up the training as well. So they use backpropagation, and along with backpropagation is batch training or stochastic gradient descent. And it's called stochastic gradient descent because the path ends up like very stochastic, and stochasticness is achieved by shuffling these batches around. Does that make sense? Right, so I'm planning to make a separate stream where we can try to apply that. You can also optimize L1. Oh yeah, we didn't even apply any headway optimizations like anywhere. Like what we're doing so far, right, what we're doing so far is when it comes to metric multiplication, so that's literally how we do that. Like that's the whole matrix multiplication on CPU because we're learning things. Right, and there is a lot of like low-hanging fruits to actually speed up this entire thing, right? But I intentionally implement everything in a very dumb way to just learn, right? So because I think you know, implementing everything from scratch and just like making it work at least slow is actually very educational, because again, there is no point in moving fast if you don't know the direction, right? So again, it's just like, why don't I use GPU acceleration? Why don't I use fancy algorithms? Why don't I go fast? Zojin, you have to go fast. Zojin, why are you so slow? What's the point of going fast if you don't know the direction? I'm learning, trying to implement the most optimal, the most performant algorithms when you learn the concept is actually very dangerous for educational value. So it doesn't have an educational value. Figure out the direction. And once you figure it out, only then, like call a taxi or something, I don't know, just to go faster, right? You know what I mean? So that's basically what it is. By the way, and there is another low-hanging fruit. You know what I mean? We can try that. Yep. So it's gonna take some time to build this entire thing. Is it gonna be faster? Feels like it's a bit faster. Yeah, it's already almost done. Yeah, it's okay. Cool. So I guess that's it for today. I hope I didn't miss any subs. Okay, so thank you Til Khan for Twitch Prime, and Nutrix Dev. Thank you so much for Twitch Prime with the message chat is cute. Chat is cute indeed. So all right, so that's it for today. Thanks everyone who's watching me right now. I really appreciate that. I hope this stream was interesting, right? I don't know how educational that was, because backpropagation is really difficult to explain in layman terms, if you know what I mean, right? Because of sheer complexity, and I want to stress that out. It's not difficult, right? It doesn't really do anything that you can't comprehend. It's just like complex, right? It's a 4-dimensional loop that you have to keep in mind. Yeah, thanks everyone for watching. See you all on the next session. Love you.